Hello there and welcome to Life Beyond Seen, a place where curiosity is allowed to slow down, where science is told softly, and where the world feels a little quieter than it usually does. This space was made for moments like this one, when the day has finally loosened its grip and your thoughts are ready to drift without needing to arrive anywhere in particular. Tonight, we're turning our attention downward, far beneath the surface of the ocean, past the reach of sunlight, past the places maps usually stop paying attention to, and into one of the most extreme environments on Earth. The ocean is familiar to most of us in a very specific way. We know the sound of waves rolling in. We know the feeling of cold water around our ankles, the way sand shifts underfoot, the way salt lingers on skin. Even those who have never seen the sea often carry an image of it, shaped by stories, screens, or memories borrowed from others. But that version of the ocean, the one we recognise and feel comfortable imagining, is only a thin skin stretched across something far deeper, far stranger, and far less forgiving. Beneath the surface lies a world that does not care whether it is seen, named, or understood. A place where pressure replaces gravity as the dominant force, where darkness is not the absence of light, but a permanent condition, and where life, against all reasonable expectations, continues anyway. At the very lowest point of this vast underwater landscape sits the Mariana Trench, a scar in the Earth's crust so deep that Mount Everest could be dropped inside it and still leave room to spare. And at the absolute bottom of that trench is a place that feels less like a location and more like a boundary, a point where the familiar rules of surface life quietly stop applying. This descent isn't about drama or danger. There's no rush here, no countdown, no sudden drop. It's more like sinking slowly, layer by layer, allowing the surface noise to fade while the deeper rhythms take over. The ocean does not reveal itself quickly, and it does not reward impatience. It reveals itself the way night arrives, gradually, until you realise the light is gone and you've adjusted without noticing when it happened. If this feels like a comforting pace, if the idea of learning without being pulled forward too quickly appeals to you, then spending time here will probably feel natural. A quiet like or a gentle subscription helps this calm corner continue to exist for others who might need it, but there's no urgency attached to that. This space will keep moving at its own speed regardless. Now imagine standing at the edge of the Pacific Ocean, looking out at water that appears calm and endless. From this vantage point, the surface seems like the whole story. But below that surface lies a vertical journey unlike any other on the planet. The first few meters are lively and familiar, filled with fish, shifting light, and the constant movement of waves. Then the colours begin to thin. Reds disappear first, followed by oranges and yellows, until everything takes on shades of blue and grey. Sound changes too. The chaos of surface noise softens, replaced by a quieter, heavier stillness. As depth increases, pressure begins to build in a way that is difficult to fully picture. At sea level, the atmosphere presses down on us constantly, but our bodies evolve to live with that weight, so it goes unnoticed. Underwater, pressure increases by 1 atmosphere every 10 meters. By the time you reach a depth that still feels shallow to a diver, the force surrounding you is already several times greater than what you experience on land. And this pressure doesn't stop increasing. It keeps stacking, layer after layer, until it becomes the defining feature of the environment. Light continues to fade as you descend. Eventually, the last traces of sunlight vanish completely. This isn't the dimness of dusk or the shadowy darkness of a moonless night. It's a kind of darkness that doesn't fluctuate, doesn't shift, and doesn't respond to time. Once you pass a certain depth, the sun may as well not exist. The ocean here is not waiting for morning. Temperature drops too, settling into a near-freezing consistency that remains stable year-round. Seasons lose their meaning in a place where the sun never reaches and weather cannot penetrate. The water becomes heavier, colder, and more still, pressing in from all sides with a weight that cannot be resisted, only endured. Most of the ocean lies within this darkness. The shallow coastal zones that feel so expansive to us make up a surprisingly small fraction of the total marine environment. The majority exist far below, in regions humans rarely see and almost never visit. These depths are not empty, they are simply unfamiliar. As the descent continues, the seafloor appears in places rising into underwater mountains, plateaus and ridges. Then, suddenly, it drops away. The continental shelf ends, and the Earth opens into something steeper and more dramatic. This is where trenches begin, long narrow depressions formed by tectonic plates colliding, one sliding beneath another over millions of years. The Mariana Trench is the deepest of them all. The trench stretches for thousands of kilometers, curving through the western Pacific like a slow, deliberate cut. Its deepest point, known as the Challenger Deep, lies nearly 11 kilometers beneath the ocean's surface. That number alone is difficult to connect to anything tangible. It's deeper than commercial airplanes fly above the Earth. It's deeper than the height of the tallest mountains. It represents a vertical distance so extreme that comparisons begin to lose their usefulness. At the bottom, pressure reaches more than 1,000 times what you experience at sea level. This is not pressure that squeezes gently or gradually. It is constant, absolute, and crushing. Any unprotected object placed there would be destroyed almost instantly. Air-filled spaces collapse, materials deform, structures designed for surface conditions simply cannot survive. And yet, this place exists, quietly, continuously, whether anyone is there to observe it or not. For a long time, scientists assumed that nothing could live at such depths. The combination of crushing pressure, freezing temperatures, and complete darkness seemed incompatible with biology as it was understood. Life, it was believed, required sunlight directly or indirectly. Without photosynthesis, ecosystems would fail. Without ecosystems, survival would be impossible. That assumption turned out to be wrong. Life at extreme depths does not follow surface rules. It does not rely on sunlight. It does not prioritize speed, color, or abundance. Instead, it adapts to scarcity, stability, and pressure in ways that feel almost counterintuitive. At the bottom of the Mariana Trench, organisms exist that are built not to resist pressure, but to incorporate it into their very structure. Their cells, proteins, and membranes are arranged in ways that would fail instantly if brought to the surface. This kind of life moves slowly. Energy is precious. Food arrives rarely, drifting down from above as fragments of organic matter, dead plankton, and waste from shallower ecosystems. These scraps, sometimes called marine snow, take days or weeks to reach the trench floor, and by the time they arrive, they've already been picked over repeatedly. What remains is thin, scattered, and unpredictable. Yet even here, something waits. The sea floor at the bottom of the trench is not smooth or barren. It is covered in fine sediment, shaped by slow currents and occasional disturbances. Tiny organisms live within this sediment, feeding on what little organic material is available. Larger creatures move above it, conserving energy, drifting rather than swimming when possible. There is no silence in the absolute sense. Water carries sound efficiently, and even at these depths, vibrations travel vast distances. The sounds are not familiar. There is no crashing surf, no wind, no rain. Instead, there are distant echoes, low-frequency movements, the occasional rumble of geological activity far below the crust. The ocean is never truly still. It is simply quieter in ways that are hard to notice. Human presence at the bottom of the Mariana Trench is extraordinarily rare. Only a handful of missions have ever reached it, and each one required years of planning, specialized engineering, and a willingness to accept that many things could go wrong. The vehicles capable of withstanding such pressure are thick-walled, compact, and meticulously designed. Every material choice matters. Every seal, every joint, every surface is tested repeatedly before being trusted with the descent. When humans finally did reach the bottom, they did not find a dramatic landscape or sudden revelation. They found mud, darkness, cold, and life continuing quietly, exactly as it had for millions of years. The significance of that discovery was not in spectacle, but in confirmation. Life does not need comfort. It needs consistency and time. There is something grounding about that realization. At the deepest point on Earth, in conditions that feel utterly hostile to surface existence, life persists without fanfare. It does not announce itself. It does not perform. It simply exists, adapted perfectly to a place most of the planet will never see. As this journey continues, the focus will narrow further, from the broad descent through the ocean's layers to the specific conditions at the trench floor, from the idea of depth to the reality of what occupies it, from the environment itself to the organisms shaped by it, and eventually to the subtle ways human activity has reached even here. For now, the descent continues, steady and unhurried, leaving the surface far above and allowing the deep to define its own terms. Most of what we believe we know about the ocean comes from a very thin layer at the top, a boundary zone where air meets water and where human presence feels natural enough to forget how fragile it actually is. This upper skin of the ocean is where ships travel, where storms leave their marks, where sunlight still reaches and warmth still lingers. It is the ocean of postcards, documentaries, childhood memories, and weekend plans. It feels vast to us, unpredictable at times, powerful even, but it is also familiar enough that we assume it represents the whole. That assumption is understandable. Humans are surface creatures. We evolved to walk under an open sky, to breathe air, to rely on sunlight and fire. Even when we enter the ocean, we do so briefly and cautiously. We wade, we swim, we dive a little, but we always return upward. Our technology reflects this bias. Most boats float. Most research happens near coasts. Most underwater footage comes from depth that would still allow a diver to surface safely with the right equipment. The deeper ocean remains largely out of sight, and because it is out of sight, it quietly slips out of mind. When people picture the ocean, they often imagine coral reefs filled with colour, schools of fish moving in synchronized flashes, whales breaching against blue horizons. These images are not wrong, but they are incomplete. Coral reefs, for all their complexity and beauty, exist only in shallow sunlit waters. They depend entirely on light. Remove that light and the reef cannot survive. The same is true for most of the marine life people recognise and name easily. Dolphins, turtles, sharks, and most fish species live within a narrow vertical range compared to the total depth of the ocean. In fact, the part of the ocean that receives enough sunlight for photosynthesis, known as the photic zone, extends only about 200 meters down. Beyond that, light diminishes rapidly. By 1,000 meters, sunlight is effectively gone. Everything below that point exists in permanent darkness. When you realize that the average depth of the ocean is nearly 4,000 meters, it becomes clear how small the familiar portion really is. The surface ocean feels dynamic because it is shaped constantly by wind, waves, weather systems, and temperature changes. It is restless and responsive. The deep ocean, by contrast, changes slowly. Temperatures remain near freezing year-round. Currents move with patience, measured in years rather than hours. Storms that churn the surface leave little trace far below. This stability makes the deep ocean feel alien, not because it is chaotic, but because it is steady in ways we're not used to experiencing. There is also a psychological element to how we misunderstand the ocean. We tend to think horizontally rather than vertically. When we imagine distance, we picture miles across a map, not kilometers straight down. The ocean encourages this habit by presenting a flat surface that stretches to the horizon. It hides its depth so effectively that even standing on a cliff overlooking deep water, it can be hard to grasp what lies beneath. The surface gives no visual cues about how far down the seafloor might be. Calm water can cover immense depth without revealing anything about it. Maps reinforce this illusion. Traditional maps show oceans as empty blue spaces separating continents, sometimes decorated with labels or depth shading, but rarely with the same detail given to land. Mountains, rivers, cities, and borders are carefully drawn above water, while the seafloor is smoothed into gradients. This creates the impression that the ocean floor is relatively uniform, when in reality it is as varied as any terrestrial landscape. There are underwater mountain ranges longer than the Andes, valleys deeper than the Grand Canyon, plains broader than deserts, and trenches that descend beyond anything found on land. The ocean we think we know is also shaped by accessibility. Fishing fleets operate mostly in relatively shallow waters. Submarine cables, oil rigs, and offshore platforms are limited by depth and cost. Even military submarines, built to withstand pressure and remain hidden, operate within constraints far above the deepest parts of the ocean. Human industry touches the sea constantly, but almost always from above or just below the surface. Because of this, our cultural relationship with the ocean often swings between comfort and fear, but rarely curiosity about its full depth. The ocean is portrayed as a place of leisure or danger, not as a layered environment with rules that change dramatically as you descend. Beaches are associated with relaxation. Storms and shipwrecks symbolize chaos. The abyss, when it appears at all, is framed as monstrous or unknowable, a blank space filled with imagined threats rather than studied realities. Even language reflects this bias. We talk about the sea as if it were a single place, rather than a stacked series of environments. We use words like deep casually, without attaching them to specific conditions. Deep water might mean a few meters to a swimmer, a few hundred meters to a diver, or several kilometers to a geologist. The same word stretches to cover vastly different realities. Science itself was slow to move beyond the surface. For centuries, studying the deep ocean was limited by technology. Early attempts to sample deep waters relied on weighted lines and dredges that scraped the seafloor blindly. These tools brought back fragments, organisms crushed or damaged by pressure changes, offering hints but little context. It was difficult to know where exactly samples came from, or how they lived before being hauled upward. This lack of context fueled misconceptions. Many early scientists believed the deep ocean was largely lifeless, a stagnant zone where organic material accumulated but did not support active ecosystems. This idea, sometimes called the azoic hypothesis, persisted well into the 19th century. It was supported by the assumption that sunlight was essential for life, and that extreme pressure would prevent biological processes. The first cracks in this belief appeared when deep-sea organisms were recovered intact enough to study. Strange fish, translucent crustaceans, and unfamiliar invertebrates began to challenge surface-based assumptions. Still, without direct observation, these discoveries felt abstract, disconnected from a living environment. It was only with the development of deep-sea submersibles and remotely operated vehicles that scientists could finally see the deep ocean as it is, not just as fragments pulled into the light. What they found was not emptiness, but adaptation, not chaos, but quiet persistence. The deep ocean operates on principles that feel unfamiliar because they are optimized for conditions humans never evolved to face. Energy moves slowly. Life prioritizes efficiency over speed. Growth is gradual. Reproduction can take years or decades. Predation exists, but it is measured and often opportunistic rather than aggressive. The ocean we think we know is bright, noisy, and active. The ocean that dominates the planet is dark, cold, and patient. It covers more than 70% of Earth's surface, and most of its volume lies far below the reach of sunlight. In terms of sheer living space, the deep ocean represents the largest habitat on the planet, yet it remains the least explored. This disconnect matters because it shapes how we treat the ocean as a whole. Environmental concern often focuses on visible issues, coral bleaching, oil spills, plastic waste floating at the surface. These problems are real and serious, but they are not the full picture. Human influence extends downward through sinking debris, chemical runoff, and changes in temperature and circulation patterns. The deep ocean is not isolated from surface activity. It is buffered, delayed, but not immune. Understanding the Mariana Trench, or any deep-sea environment, requires letting go of the surface-centric mindset. It requires accepting that the ocean is not a single place with uniform conditions, but a vertical world with layers that behave almost like separate planets, stacked on top of one another. The rules that apply at the surface do not simply weaken with depth, they change. As attention shifts downward, the familiar markers of time and place begin to blur. Day and night lose meaning, seasons fade, weather becomes irrelevant. What remains is a steady environment governed by pressure, chemistry, and gravity. To understand what exists at the bottom of the Mariana Trench, it helps first to recognize how little of the ocean we actually know, and how much of our intuition is shaped by a layer that represents only a small fraction of the whole. The descent continues not as a dramatic plunge, but as a gradual reframing of expectations. The deeper the focus goes, the more the ocean stops resembling the version stored in memory and starts revealing itself as something quieter, older, and far more extensive than surface experience ever suggests. Depth is one of those ideas that feels simple until you try to hold on to it for too long. On land, depth usually has a clear reference point. A basement is a few meters below ground. A canyon might be a kilometer deep. A mine shaft descends until the air thins and the rock presses close. These are distances that can be walked, measured, or at least imagined with some effort. The ocean disrupts that sense of scale almost immediately. It presents a surface that looks flat and calm, then hides everything else beneath it, offering no visual cues about what lies below. You could be floating above water that is 10 meters deep or 10,000, and without instruments, you would feel almost the same. When people say something is deep, they often mean it metaphorically. A deep conversation, a deep thought, a deep sleep. In everyday language, depth suggests complexity or intensity, not a specific measurement. The ocean, however, forces depth to become literal. It is not symbolic. It is physical, measurable, and unforgiving. And yet, even with numbers attached, it remains difficult to grasp. The average depth of the ocean is about 3,700 meters. That alone is already beyond what most people can comfortably imagine. Commercial airplanes cruise at around 10,000 meters above the ground, a height that feels remarkable when you look down through a window. The deepest point of the Mariana Trench reaches nearly 11,000 meters below sea level. That means the vertical distance from the ocean's surface to its deepest point is comparable to the distance from the ground to where airplanes fly. Except instead of thinning air and expanding sky, it is filled entirely with water, growing heavier with every meter. Part of the challenge in understanding ocean depth is that humans are not built to experience vertical environments. Gravity keeps us oriented to a surface. We move across landscapes, not through them. Even tall structures like skyscrapers or mountains still rely on a base, a ground reference that keeps up and down clearly defined. In the ocean, that reference disappears almost immediately. Once you leave the surface, there is no visual anchor. Down becomes a direction without landmarks. Pressure plays a central role in turning depth from an abstract number into a physical reality. At sea level, the pressure of the atmosphere is about 1 atmosphere, roughly 101 kilopascals. This pressure exists all around us, but because it is balanced inside and outside our bodies, we don't feel it. Water, however, is much denser than air. As you descend underwater, the weight of the water above you adds pressure steadily and predictably. Every 10 meters adds another atmosphere of pressure. At 100 meters, the pressure is 11 atmospheres. At 1,000 meters, it is about 101. At the bottom of the Mariana Trench, the pressure exceeds 1,000 atmospheres. That is equivalent to having the weight of about 50 jumbo jets pressing down on an area the size of a human body. This is not pressure that fluctuates or eases. It is constant, pressing from all directions with no gaps or relief. For the human body, even a fraction of that pressure is dangerous. Without protection, descending more than a few dozen meters can cause serious injury or death due to pressure-related effects on the lungs, blood, and nervous system. This is why deep-sea exploration relies on specialized vehicles rather than divers. The ocean does not allow gradual adaptation beyond certain limits. It demands either full protection or none at all. Depth also affects light in a way that reshapes perception. Sunlight entering the ocean is scattered and absorbed as it travels downward. Different wavelengths disappear at different rates. Red light is absorbed first within the top few meters. Orange and yellow follow. Green lasts longer, which is why shallow water often looks greenish or blue-green. By around 200 meters, nearly all sunlight is gone. Beyond that, darkness is not a phase but a permanent condition. This loss of light removes one of the most important reference points humans rely on. Without light, there is no shadow, no horizon, no visual gradient to suggest distance or shape. Objects do not fade gradually into darkness the way they do at night on land. They simply stop being visible. In this environment, depth becomes something you know intellectually rather than something you can see. Sound behaves differently as well. In water, sound travels faster and farther than in air. The deep ocean carries low-frequency sounds across vast distances, sometimes thousands of kilometers. Whales communicate this way, using sound to bridge distances that would be impossible visually. For humans, however, this creates a strange sensory mismatch. You might hear something long before you could ever see it, and often without being able to tell where it came from. Temperature adds another layer to the experience of depth. Surface waters are warmed by the sun and cooled by the air, creating variation across seasons and latitudes. Below a certain depth, temperature stabilizes near freezing. In much of the deep ocean, the water remains just above 0 degrees Celsius year-round. This cold is not sharp or biting like winter air. It is steady and enveloping, contributing to the sense that time itself moves more slowly. As depth increases, time does begin to feel different, not because it actually changes, but because the cues we use to track it disappear. There is no sunrise or sunset, no weather, no daily cycle. Biological rhythms adapt to this constancy, but for humans, it creates a sense of suspension. The deep ocean does not mark time the way the surface does, it simply exists. One of the reasons the Mariana Trench feels so extreme is not just its depth, but its steepness. Trenches are narrow compared to their depth, with sides that drop sharply rather than gradually. This creates a sense of sudden descent rather than a long slope. In some places, the trench walls fall almost vertically, plunging from depths that are already far below the surface into even greater darkness. It is not a gentle deepening, it is a fall. This verticality challenges another human instinct, the assumption that the Earth's surface is relatively smooth. On land, the tallest mountains and deepest valleys vary by only a few kilometers. The ocean floor exaggerates these differences dramatically. Underwater mountain ranges rise thousands of meters above the seafloor, while trenches cut equally deep below it. The vertical relief of the ocean floor rivals, and in some cases exceeds, that of the continents. To make sense of this, scientists often rely on comparisons. Mount Everest is about 8,148 meters tall. If you placed it at the bottom of the Mariana Trench, its peak would still be more than 2 kilometers below the ocean's surface. These comparisons are useful, but they also flatten the experience into numbers and images that still remain abstract. Knowing that something is taller or deeper than Everest does not necessarily make it feel real. Another way to think about depth is through the concept of zones. Oceanographers divide the ocean vertically into layers based on light, temperature, and ecological function. These zones are not strict boundaries but gradual transitions. The epipelagic zone, where sunlight supports photosynthesis, extends down about 200 meters. Below that lies the mesopelagic, or twilight zone, where faint light remains but photosynthesis cannot occur. Deeper still is the bathypelagic, where darkness is complete. Below that are the abyssopelagic and hadal zones, the latter including trenches like the Mariana. The hadal zone begins at around 6,000 meters. Everything below that point exists in conditions few organisms experience elsewhere. Pressure is extreme, food is scarce, temperature is low, yet life persists, adapted not just to survive but to function normally under these conditions. For these organisms, this depth is not extreme, it is home. For humans, however, depth remains a boundary. Our technology allows us to visit briefly, observe, sample, and return. But we do not live there. We do not adapt over generations to those conditions. Our relationship with deep ocean depth is observational, not experiential. We rely on instruments, cameras, and sensors to translate what exists there into something we can understand. Even those instruments face limits. Extreme pressure challenges electronics, materials, and mechanical systems. Every descent to the bottom of the Mariana Trench is a calculated risk. The deeper you go, the fewer options you have if something fails. There is no quick rescue, no easy ascent. Depth is not just distance. It is isolation. This isolation has contributed to the deep ocean's reputation as unknowable. In reality, it is not unknowable, but it requires patience, resources, and humility. Each meter downward strips away assumptions carried from the surface. Each zone reveals that the rules we rely on are local, not universal. Understanding how deep the Mariana Trench really is means letting go of the idea that depth is just a number. It is a set of conditions layered on top of one another. Pressure, darkness, cold, isolation and time all intensify together. Depth is cumulative. It is not just how far down you go, but how much the environment changes as you do. As attention continues to move downward, the scale becomes less about comparison and more about consequence. What matters is not how deep the trench is relative to mountains or aircraft, but what that depth does to matter, to life, and to the limits of exploration. The deeper the focus goes, the more the ocean stops being a backdrop and starts becoming an active force shaping everything within it. The descent does not end with understanding depth. It only reframes the question. Once depth stops being abstract, the next question naturally follows. Not how deep it is, but what that depth allows and forbids, what survives there, and how the planet itself behaves when pushed to such extremes. When people think about the shape of the Earth, they usually picture continents outlined on a map, mountain ranges rising above plains, rivers carving their way toward the sea. This surface-focused view is so deeply ingrained that it's easy to forget the planet has another face entirely, one that lies hidden beneath the ocean. The Mariana Trench belongs to that hidden face. It is not just a deep place in the water, it is a structural feature of the Earth itself, a direct expression of the forces that shape the planet from the inside out. Beneath the calm or stormy surface of the Pacific Ocean, the Earth's crust is in constant motion. It moves slowly enough that a human lifetime barely registers the change, but relentlessly enough that entire oceans open and close over geological time. The Mariana Trench exists because the Earth is not a solid shell. It is broken into massive slabs of rock called tectonic plates, floating on a semi-molten layer beneath them. These plates drift, collide, pull apart and slide past one another, reshaping the planet inch by inch. The trench marks one of the most dramatic interactions between two of these plates. In this region of the Western Pacific, the Pacific Plate is moving westward and downward, colliding with the smaller Mariana Plate. Instead of crumpling upward to form mountains, as happens when two continental plates collide, the denser oceanic Pacific Plate bends and sinks beneath the Mariana Plate. This process is known as subduction. and it is one of the primary ways the Earth recycles its crust. As the Pacific plate is forced downward, it creates a long, narrow depression in the seafloor. That depression is the Mariana Trench. It is not a crack or a hole in the Earth, but a bending, flexing zone where solid rock is pushed into the planet's interior. The trench stretches for more than 2,500 kilometers, curving gently along the boundary between the plates. Its depth is not uniform. Like a valley on land, it has variations, ridges, slopes, and a lowest point where the bending is most extreme. This lowest point, the Challenger Deep, represents the deepest known location on Earth's surface. But calling it a surface is misleading. It is more accurate to think of it as the deepest exposed edge of the crust before it disappears into the mantle. Beneath the trench floor, the subducting plate continues its descent, carrying minerals, water, and heat downward into regions humans will never directly observe. The shape of the trench tells a story about stress and flexibility. Although rock feels rigid and unyielding to us, over geological timescales it behaves more like a slow-moving, extremely viscous material. Under immense pressure and heat, it can bend without breaking, fold without shattering. The Pacific plate does exactly that as it approaches the trench, bowing downward before plunging into the Earth. This bending creates not only the trench itself, but also a rise on the seafloor farther out, a subtle bulge formed by the plate flexing upward before it dives. This means the trench is part of a larger deformation zone, not an isolated feature. It is connected to underwater volcanoes, earthquake zones, and deep mantle processes that extend hundreds of kilometers below the seafloor. The Mariana region is seismically active, though not always in ways humans can easily feel. Earthquakes occur deep within the subducting plate, sometimes at depths far greater than those seen beneath continents. These deep focus earthquakes challenge assumptions about how rock behaves under pressure, revealing that even at extreme depths the Earth can still fracture and release energy. The shape of the Earth beneath the Mariana Trench also reveals something counterintuitive. The deepest part of the ocean does not sit above the thinnest crust. In fact, oceanic crust is relatively thin compared to continental crust, averaging about 7 kilometers thick. Beneath the trench, this crust is being pulled downward, but it remains intact as a coherent slab for a long distance into the mantle. This slab influences the flow of material deep within the Earth, redirecting heat and altering convection patterns that help drive plate motion globally. In this sense, the trench is not just a local feature, it is part of a planetary system. Movements here affect processes elsewhere, even if the connections are indirect and delayed by millions of years. The sinking of the Pacific plate contributes to mantle circulation, which in turn influences volcanic activity in distant regions. The Earth beneath the trench is not isolated, it is deeply connected. Above this geological machinery lies the ocean itself, filling the trench with water that presses down with enormous force. The shape of the trench determines how that water settles, how sediments accumulate, and how currents behave at extreme depths. Fine particles rain down from the upper ocean, settling slowly into the trench and creating thick layers of mud. Over time, these sediments can be scraped off the subducting plate, compressed, and eventually uplifted elsewhere, forming new land long after the trench itself has moved or vanished. The seafloor at the bottom of the trench is not smooth or static. It bears the marks of tectonic strain, subtle ridges, cracks, and variations created by the bending of the plate and the slow accumulation of sediment. These features are small compared to mountains or canyons on land, but in the deep ocean, even small variations matter. They influence where organisms settle, how nutrients accumulate, and how water moves close to the bottom. What makes the Mariana Trench especially striking is how sharply it contrasts with the surrounding seafloor. The Pacific Ocean basin is already deep, averaging several kilometers below sea level. The trench plunges far below that baseline, creating a sudden vertical drop that feels almost unnatural when viewed on a profile. This dramatic change is a reminder that the Earth's surface is not evenly distributed around a single level. It is warped and shaped by forces operating far below our feet. If the oceans were drained away, the Mariana Trench would not appear as a neat canyon carved by erosion. It would look more like a long dark wound in the planet's crust, flanked by sloping walls and surrounded by a landscape already far below what we consider normal ground level. It would be a place where gravity feels different, where air pressure would be crushing if air could even exist there, and where the sky would feel impossibly distant. Understanding the shape of the Earth beneath the trench also reframes how we think about stability. From a human perspective, the planet feels solid and dependable. The ground beneath us seems fixed. The trench reveals a different truth. The Earth is active, restless, constantly reshaping itself in ways that rarely intersect with daily life but define the long-term fate of continents and oceans. The Mariana Trench is relatively young in geological terms, formed over tens of millions of years. Before it existed, the plates involved were arranged differently. In the distant future, the trench will likely disappear as plate boundaries shift and ocean basins change. The Pacific Ocean itself may shrink or vanish, replaced by new oceans forming elsewhere. The trench is not permanent. It is a snapshot of an ongoing process. This impermanence adds another layer to the meaning of depth. The deepest place on Earth today may not be the deepest forever. Depth is not an absolute property of the planet, but a temporary outcome of moving plates and changing boundaries. The Earth beneath us is not finished. It is still becoming. As attention continues to move downward and inward, the trench stops feeling like an endpoint and starts to feel like a gateway. It is a place where the surface world meets the deeper engine of the planet. What exists at the bottom is shaped not only by water and pressure, but by the slow, powerful movements of rock far below. To understand life, chemistry, and even human traces at the trench floor, it helps to remember that everything there rests on a foundation that is itself in motion, bending, sinking, and transforming over spans of time that dwarf human history. The descent continues, not just into deeper water, but into the structure of the Earth itself, where shape, pressure, and motion converge to create conditions unlike anywhere else on the planet. By the time the descent reaches the deepest parts of the ocean, three conditions dominate everything that exists there: pressure, darkness, and scarcity. These are not background features. They are the rules. They decide what can exist, how it can function, and how long it can endure. At the bottom of the Mariana Trench, survival is not about strength, speed, or intelligence in any familiar sense. It is about compatibility. Either an organism fits the conditions perfectly, or it does not exist there at all. Pressure is the most immediate and unforgiving of these conditions. It is constant, inescapable, and absolute. At nearly 11,000 meters below the surface, the pressure exceeds 1,000 atmospheres. That number is often repeated, but its meaning is easy to lose. Pressure at this level is not simply heavy, it is structurally transformative. Materials behave differently, chemical reactions shift, physical laws remain the same, but their consequences change dramatically. For living organisms, pressure affects every level of biology. Cell membranes, proteins, enzymes, and DNA must all remain stable under forces that would instantly destroy surface-adapted life. In shallow water, cell membranes are relatively flexible, allowing molecules to pass in and out with ease. Under extreme pressure, that flexibility becomes a liability. Membranes can become too rigid or collapse entirely unless their chemical composition is precisely tuned. Deep-sea organisms solve this problem in ways that are invisible from the outside. Their membranes contain different ratios of fats and proteins, arranged to maintain fluidity despite compression. Their enzymes, which drive chemical reactions necessary for life, are structured to function efficiently under pressure that would cause surface enzymes to malfunction or unfold. These adaptations are not optional. Without them, even the most basic cellular processes would fail. Proteins, in particular, are sensitive to pressure. Their three-dimensional shapes are essential to their function, and pressure can force them into configurations that no longer work. At the bottom of the Mariana Trench, proteins must be stable enough to hold their shape, while still remaining flexible enough to do their job. This balance is achieved through subtle changes in amino acid sequences, changes that have accumulated over millions of years of evolution under consistent pressure. Darkness is the second defining rule, and unlike pressure, it is absolute rather than incremental. Once sunlight disappears, it does not return. There are no cycles, no dawns or dusks, no seasonal variations in light. Darkness in the deep ocean is not something that happens at night. It is the default state of existence. Without sunlight, photosynthesis is impossible. This removes the foundation of most surface ecosystems. Plants, algae, and photosynthetic bacteria cannot survive here. Instead, deep-sea ecosystems rely on other energy sources. The most common is organic matter that sinks from above. Dead plankton, fecal pellets, fragments of plants and animals all drift downward slowly, forming a thin, irregular rain of nutrients. By the time this material reaches the trench floor, it has already been consumed and broken down multiple times. What remains is low in energy and unpredictable in supply. Organisms living at these depths cannot rely on frequent meals. They must be able to endure long periods without food, conserving energy whenever possible. Some deep-sea life sidesteps this limitation by relying on chemosynthesis rather than photosynthesis. In certain regions, particularly near hydrothermal vents or cold seeps, bacteria use chemical energy from compounds like hydrogen sulfide or methane to produce organic matter. However, the Mariana Trench is not rich in these features compared to other deep-sea environments. Most life there depends on the slow trickle from above. This scarcity shapes behaviour. Movement is minimised, metabolisms are slow, growth rates are measured in years or decades rather than weeks or months. Reproduction is infrequent and often involves producing fewer offspring, each with a higher chance of survival. In an environment where energy is limited, efficiency becomes the primary currency. Vision, a dominant sense for surface animals, becomes largely irrelevant. Eyes, if present at all, are often reduced or adapted for detecting faint bioluminescence rather than reflected sunlight. Many trench-dwelling organisms are blind. Others have light-sensitive cells that help them detect the glow of nearby creatures rather than see shapes or colours. Bioluminescence plays a complex role in the deep ocean, but at the very bottom of the trench it becomes less common. Producing light requires energy, and energy is precious. Where bioluminescence does occur, it is often subtle, brief, and highly specific in purpose. It may be used to attract prey, deter predators, or communicate with potential mates. It is not decorative. Nothing here exists without function. The absence of light also changes how space is perceived. Without visual cues, organisms rely on other senses to navigate their environment. Touch, vibration, and chemical detection become primary. Many deep-sea creatures have elongated antennae, sensitive skin, or specialized receptors that allow them to detect minute changes in water movement or chemical composition. Sound, too, becomes important. Although sound travels efficiently in water, the deep ocean is not loud in the way the surface can be. There is no crashing surf or wind-driven noise. Instead, the soundscape is dominated by low-frequency signals that can travel vast distances. Some organisms are adapted to detect these vibrations, using them to sense the presence of other animals or geological activity. Pressure and darkness together create an environment where rapid reactions and sudden changes are rare. This stability allows certain adaptations to persist over long periods. Deep-sea organisms often show little change over evolutionary timescales compared to their surface counterparts. When conditions remain constant, there is less pressure to change. Evolution still occurs, but it moves slowly, shaped by subtle shifts rather than dramatic upheavals. Survival at the bottom of the Mariana Trench also requires coping with isolation. Population densities are low. Encounters with other individuals of the same species may be rare. This influences reproductive strategies. Some organisms are hermaphroditic, capable of self-fertilization if necessary. Others release gametes into the water, relying on chance encounters in a vast dark environment. Still others use chemical signals to attract mates from a distance. Predation exists, but it is not constant. When prey is scarce, predators cannot afford to chase every opportunity. Many trench-dwelling predators are ambush specialists, waiting patiently for long periods rather than actively hunting. Their bodies are often soft and gelatinous, reducing energy costs and allowing them to withstand pressure without rigid structures that could fail. Bones, shells, and other hard structures present a challenge under extreme pressure. While some deep-sea organisms do have shells or exoskeletons, these are often thinner or composed of materials that behave differently under compression. In many cases, rigidity is replaced by flexibility. Soft bodies distribute pressure evenly, reducing the risk of structural failure. Fish living at extreme depths often lack swim bladders, the gas-filled organs that help surface fish control buoyancy. Gas-filled spaces collapse under pressure. Instead, these fish rely on oils or specialized tissues to maintain neutral buoyancy. Their muscles are less dense, their skeletons lighter, their overall structure optimized for an environment where floating is a matter of chemistry rather than air. Even basic processes like respiration are affected. Oxygen is present in deep water, but at lower concentrations than at the surface. Deep-sea organisms have adapted to extract oxygen efficiently, often with larger gill surfaces or specialized blood proteins that bind oxygen more readily. These adaptations allow them to survive in conditions that would quickly exhaust surface animals. What is striking about these survival strategies is how interconnected they are. Pressure influences chemistry. Chemistry influences metabolism. Metabolism influences behavior. Behavior influences reproduction. Survival at the bottom of the Mariana Trench is not achieved through a single adaptation, but through a tightly integrated system where every aspect of an organism's biology is tuned to the environment. Humans, by contrast, cannot adapt biologically to these conditions within any meaningful time frame. Our survival in the deep ocean is entirely technological. Submersibles must be built to withstand pressure using thick hulls, often spherical in shape to distribute force evenly. Electronics must be protected from compression and corrosion. Life support systems must recreate surface conditions inside a sealed environment, creating a small bubble of familiarity surrounded by overwhelming force. Even with this technology, human presence at extreme depth is brief, hours at most. We visit, observe, collect data, and leave. The deep-sea organisms remain, continuing their slow, steady existence long after the lights of a submersible fade. Darkness also shapes how humans perceive these environments. Without natural light, everything must be illuminated artificially. Cameras show only what their beams touch, creating the illusion that the surrounding darkness is empty when it is simply unseen. This selective visibility can distort perception, making the deep ocean feel more barren than it is. In reality, life at the trench floor is sparse but persistent. It does not form dense forests or bustling reefs. It exists in scattered pockets, adapted to a lifestyle where waiting is often more effective than searching. The rules of survival favour patience over speed, efficiency over abundance, and resilience over growth. These rules also make the deep ocean vulnerable in specific ways. Because organisms grow slowly and reproduce infrequently, populations recover slowly from disturbance. A disruption that might be temporary at the surface can have long-lasting effects at depth. Recovery times can span decades or centuries. Understanding pressure, darkness, and scarcity as governing forces helps explain why the bottom of the Mariana Trench feels so different from any surface environment. It is not just deeper. It operates under a different logic. Survival is not about conquering the environment or adapting quickly to change. It is about fitting so precisely into the existing conditions that change is barely necessary. As attention continues to move deeper into the specifics of what exists at the trench floor, these rules remain constant. Pressure does not ease, darkness does not lift, resources do not become abundant. Everything that exists there does so because it has learned, over immense spans of time, how to exist under these constraints without resistance. The descent continues with this understanding in place, setting the stage for encountering the first direct witnesses to these rules in action, the organisms themselves, shaped quietly by forces that never rest. For most of human history, the deepest parts of the ocean existed only as an idea. Sailors crossed vast stretches of water without knowing what lay beneath their hulls. Philosophers speculated, cartographers left blank spaces. The deep sea was not something to be seen, only imagined, often as an abyssal void or a place filled with monsters born from fear rather than evidence. Even as science advanced, even as microscopes and telescopes extended human vision outward and inward, the deepest ocean remained stubbornly out of reach. Sounding lines were the first serious attempt to measure depth. Weighted ropes lowered from ships gave numbers where none had existed before. These measurements were slow, imprecise, and often misleading. Currents could pull the line at an angle, the rope could stretch, the weight might never truly reach the bottom. Still, they hinted at something extraordinary. Depths far greater than anyone expected. Valleys in the seafloor that seemed to descend without end. But these were still abstractions. No one had seen the bottom. No one knew what, if anything, lived there. The idea of actually sending a human being into the deep ocean was once considered unrealistic, even reckless. Pressure alone seemed like an insurmountable obstacle. Early submarines operated near the surface. Diving bells allowed short descents, but were limited and dangerous. The deeper one went, the more unforgiving the ocean became. Metal buckled, glass shattered, air supplies failed. Each attempt reinforced the sense that there was a hard boundary humans could not cross. That perception began to change in the mid-20th century, driven by advances in materials science, engineering, and a growing scientific curiosity about the deep ocean. If humans could build structures strong enough to withstand atmospheric pressure at high altitudes, perhaps they could also build vessels capable of withstanding pressure from all sides. The challenge was not just strength, but shape. Flat surfaces fail under pressure. Curves distribute force. This realization led to a design choice that would define deep-sea exploration for decades: the sphere. A spherical pressure vessel experiences stress evenly. There are no corners where force can concentrate. This simple geometric truth made it possible to imagine a vehicle that could descend into the deepest parts of the ocean without collapsing. The question was whether such a vessel could be built, launched, controlled, and safely returned. The first successful answer to that question came in 1960, with the bathyscaphe Trieste. Designed by Swiss engineer Auguste Piccard and later acquired and modified by the United States Navy, Trieste was not sleek or fast. It was functional, experimental, and unapologetically strange in appearance. A gasoline-filled float provided buoyancy. Beneath it hung a steel pressure sphere just over 2 meters in diameter, thick-walled and heavy, containing barely enough room for 2 people to sit. On January 23, 1960, Trieste began its descent into the Challenger Deep. Inside the sphere were Jacques Piccard, Auguste's son, and US Navy Lieutenant Don Walsh. As the surface faded above them, they entered a world no human had ever directly seen. The descent took nearly 5 hours. There was no view in the way people might imagine it. Outside the small porthole was darkness, illuminated only by the submersible's lights, which revealed little more than drifting particles and occasional flashes of movement. As they descended, the pressure increased steadily. At one point, a loud cracking sound echoed through the sphere. One of the outer plexiglass windows had fractured. It held, but the sound was a stark reminder that there was no margin for error. Turning back was an option, but so was continuing. They chose to continue. When Trieste finally reached the bottom, the depth gauge read approximately 10,916 metres. They had arrived at the deepest known point on Earth. The seafloor was surprisingly flat, covered in a fine, pale sediment. There were no dramatic rock formations, no towering structures, just mud gently settling, disturbed by the presence of the submersible. And then something moved. Pickard and Walsh reported seeing a flatfish-like creature swimming away from the disturbance. This observation became one of the most debated claims in deep-sea biology. Later research suggested that true flatfish likely cannot survive at such depths, and the sighting may have been a misinterpretation of another organism or a trick of light and motion. Regardless, the moment carried enormous symbolic weight. The idea that a vertebrate animal might exist at the deepest point on Earth challenged long-held assumptions about the limits of life. The two men spent only about 20 minutes on the seafloor. There was no ability to walk outside, no robotic arms, no extended exploration. The mission was about reaching the bottom, proving it could be done, and returning safely. After releasing ballast, Trieste began its ascent, rising slowly back toward the surface. When it finally emerged, humanity had, for the first time, placed human eyes at the deepest point of the planet. For decades afterward, no one repeated the feat. The Trieste dive stood alone, not because it was impossible to repeat, but because it was expensive, risky, and not easily justified in a world where other scientific priorities competed for attention. The deep ocean remained accessible primarily to robotic explorers. Remotely operated vehicles and autonomous probes could descend without risking human life, transmitting images and data back to the surface. These robotic missions transformed understanding of the deep sea. Cameras revealed organisms adapted to pressure and darkness. Sensors measured temperature, chemistry, and currents. Sample collectors retrieved sediments and biological specimens. Yet there was still something symbolically powerful about human presence. Seeing through a camera is not the same as being there. Even mediated by thick glass and artificial light, human observation carries a different psychological weight. That distinction resurfaced in the early 21st century, when interest in deep-sea exploration was renewed. Advances in materials, computing, and design made new submersibles possible. One of the most high-profile efforts culminated in 2012, when filmmaker and explorer James Cameron descended alone to the Challenger Deep in the Deep Sea Challenger submersible. This vehicle was very different from Trieste. Sleek, vertical, and equipped with high-definition cameras, robotic arms, and scientific instruments, it represented half a century of technological progress. Cameron's descent was faster, more controlled, and better documented. For nearly 3 hours he explored the seafloor, collecting samples and capturing images that would later be shared widely. What he saw reinforced earlier observations. The seafloor was covered in fine sediment. Life was present but sparse. Small shrimp-like amphipods scurried away from the lights. Microbial mats clung to surfaces. There were no dramatic creatures or sudden revelations. The environment was quiet, subdued, and consistent with what scientists had come to expect from extreme depths. In the years that followed, additional missions reached the bottom using advanced submersibles designed for repeated dives. These missions shifted the focus from novelty to data. Reaching the bottom was no longer the primary goal. Understanding it was. The presence of humans at such depths remains rare, but the idea of direct observation has reshaped how the deep ocean is perceived. It is no longer an abstract void. It is a place that has been visited, measured, and described by people who are physically present, however briefly. What is striking about these first human descents is how little they change the environment itself. Unlike surface exploration, where footprints, structures, and waste often linger, deep-sea visits are fleeting. The submersible arrives, stirs the sediment slightly, and leaves. Within hours or days, the disturbance settles. The environment returns to its baseline state as if the visit never happened. This impermanence underscores a larger truth. The deep ocean does not register human presence in the same way surface environments do. It does not accommodate us. It does not adapt to us. We are visitors passing through a system that operates on timescales and principles entirely its own. The first human eyes to look down there did not conquer the depth or unlock its secrets. They confirmed something quieter and perhaps more profound, that the deepest part of the planet is not dramatic in the way imagination suggests. It is restrained, stable, and indifferent. Life exists, but it does not perform for an audience. The Earth's processes continue, slow and steady, regardless of whether they are observed. As exploration continued, attention shifted away from the act of descent itself and toward what those brief visits revealed about the nature of life, pressure, and persistence. The human story at the bottom of the Mariana Trench is not one of dominance or transformation. It is one of momentary presence, careful observation, and respectful retreat. With that perspective in place, the focus naturally moves away from the explorers and toward what they encountered, not the machines or the milestones, but the living systems that have occupied these depths long before the first submersible was imagined, and will likely continue long after the last one descends and rises again. Life, as it is usually understood, begins with light. On the surface of the Earth, nearly every ecosystem traces its energy back to the sun. Plants capture sunlight. Animals eat plants or eat other animals that ate plants. Even decay is part of that same cycle, recycling energy that once arrived as light. This relationship is so fundamental that it shapes how we imagine life itself. Remove the sun and the system collapses, or so it seems. At the bottom of the Mariana Trench, sunlight is not absent in a temporary way. It is irrelevant. No ray has ever reached that depth. No shadow has ever moved across the seafloor. There is no memory of light, no adaptation waiting for it to return. And yet, life exists. Understanding life without light requires letting go of surface logic. It requires accepting that energy does not have to arrive in the form most familiar to us, and that ecosystems can be built on principles that feel unintuitive only because they are unfamiliar. In the deep ocean, especially at trench depths, life does not flourish. It persists. It does not expand rapidly. It endures. Without light, photosynthesis cannot occur. That removes the primary mechanism by which energy enters most ecosystems. In place of plants and algae, the deep ocean relies on alternative pathways. The most widespread of these is indirect. Organic material produced in sunlit waters slowly sinks downward, breaking apart as it goes. By the time it reaches the trench floor, it is a faint echo of its former self. Nutrients stripped, energy depleted, structure reduced to fragments and fine particles. This slow rain of debris is often called marine snow, though the term can be misleading. Snow suggests abundance, softness, and regularity. In reality, this material arrives sporadically and thinly. Some days bring more than others. Storms at the surface can send pulses downward. Seasonal blooms can increase the supply temporarily. But overall, the input is sparse. Life in the trench has adapted to this uncertainty. Organisms do not expect daily meals. They are built to wait. Their metabolisms are slow, often an order of magnitude slower than those of surface species. Heart rates are lower. Growth is measured in years. Some individuals may live for decades or longer in a state of near equilibrium, consuming just enough energy to maintain basic function. This slow pace affects everything. Movement is minimized. There is little reason to chase prey when the cost of movement outweighs the potential gain. Many trench-dwelling organisms drift rather than swim. They settle into the sediment, conserving energy, waiting for something edible to pass within reach. When food does appear, it is consumed efficiently with little waste. In the absence of light, vision loses its dominance as a sense. Eyes, when present, are often small, reduced or specialised for detecting faint glows rather than forming images. Many trench organisms are blind. Instead of sight, they rely on chemical cues, touch and vibration. Water carries information in ways air does not. A slight change in chemical composition can signal the presence of food or another organism. A vibration can indicate movement nearby. Bioluminescence, often associated with the deep ocean, becomes less prominent at trench depths. While it is common in mid-water zones, where organisms use light to attract prey or mates, the extreme scarcity of energy at the trench floor makes light production costly. Producing light requires chemical reactions that consume valuable resources. As a result, bioluminescence at these depths tends to be rare, brief, and highly targeted. Where it does occur, it serves specific functions. A sudden flash may startle a predator. A faint glow may lure an unsuspecting prey item. Communication through light is possible, but it is subtle, not constant. There is no glowing landscape, no shimmering display. Darkness remains the dominant condition. Some life at depth does not rely on falling debris at all. In certain parts of the deep ocean, including areas near tectonic activity, chemical energy replaces light as the foundation of the ecosystem. Chemosynthetic bacteria use compounds like hydrogen sulfide, methane, or ammonia to fuel their metabolism. These bacteria form the base of food webs entirely independent of sunlight. Hydrothermal vents are the most well-known example of this process. Superheated water rich in minerals emerges from the seafloor, providing energy for dense communities of organisms. However, the Mariana Trench is not dominated by such vents. Chemosynthesis does occur there, but it is more diffuse. Cold seeps, areas where methane or other chemicals slowly leak from the seafloor, support microbial life that can, in turn, support small communities of other organisms. Even here, abundance is relative. These are not lush oases in the way surface ecosystems are. They are localized concentrations of activity in an otherwise sparse environment. Life clusters where energy is available, then thins out again as conditions change. One of the most striking aspects of life without light is how little it resembles surface life in appearance. Many trench organisms are pale or translucent. Colour serves little purpose when there is no light to reflect it. Pigments that would be useful near the surface become unnecessary expenses at depth. As a result, many organisms appear ghostly, their internal structures faintly visible through their tissues. Body shapes reflect the need to withstand pressure, rather than to move quickly or efficiently through water. Soft gelatinous forms are common. Without rigid structures, pressure is distributed evenly across the body, reducing the risk of damage. Hard shells and bones are not impossible, but they require specific adaptations to avoid crushing or deformation. Fish at extreme depths often lack swim bladders, which in surface fish are used to control buoyancy. Gas-filled organs collapse under pressure. Instead, deep-sea fish rely on lipids or specialized tissues to maintain neutral buoyancy. Their muscles are less dense, their skeletons are lighter. Everything is optimized for an environment where floating is a chemical problem rather than a physical one. Reproduction without light presents its own challenges. Finding a mate in a vast, dark environment with low population density is not easy. Some species solve this by being hermaphroditic, capable of producing both eggs and sperm. Others release gametes into the water, relying on chance encounters. Some use chemical signals to attract mates from a distance, a form of communication invisible to human senses. The absence of light also affects development. Larval stages that rely on surface waters for feeding or dispersal may not exist at trench depths. Instead, offspring are often larger and more developed at birth, increasing their chances of survival in a resource-limited environment. This strategy reduces the number of offspring but increases the likelihood that each one will survive. Time behaves differently in a world without light. At the surface, day and night regulate behaviour. Seasons influence reproduction, migration and growth. At the bottom of the trench, these cycles disappear. There is no daily rhythm imposed by the sun. Biological clocks still exist, but they are regulated by internal processes rather than external cues. Life unfolds at a steady pace, largely unaffected by surface events. This constancy has evolutionary consequences. When environments are stable over long periods, there is less pressure to adapt rapidly. As a result, some deep-sea lineages show remarkable continuity over geological time. Their forms change slowly, refined rather than reinvented. They are not primitive, they are specialized, honed by consistency rather than challenge. The absence of light also shapes how ecosystems respond to disturbance. When surface ecosystems are disrupted, recovery can be relatively fast if conditions improve. Plants regrow, animals return. At depth, recovery is slow. With limited energy input and slow growth rates, rebuilding takes time. A disturbance that removes organisms from a patch of seafloor may leave it altered for decades. Human activity, though limited at these depths, has begun to leave traces. Debris sinks, chemicals disperse, even the faint presence of noise can travel long distances. Life without light is not isolated from the surface. It is buffered, delayed, but connected. There is a tendency to romanticize deep-sea life as mysterious or otherworldly. While it is certainly unfamiliar, it is also logical. Every adaptation observed at trench depths makes sense when viewed in the context of pressure, darkness, and scarcity. There is no excess. Nothing is decorative. Every feature serves a purpose or persists because it does not hinder survival. Life without light does not aspire to expand or dominate. It exists within narrow margins, balanced carefully against the energy available. This balance has been maintained for millions of years, long before humans appeared and likely long after current civilizations fade. The Mariana Trench represents an extreme case, but it is not unique in principle. It is part of a broader deep ocean system that covers most of the planet. Life without light is not an exception. It is a major mode of existence on Earth. As attention continues to move deeper into the specifics of what lives at the bottom of the trench, the focus naturally shifts from the general rules to the particular forms those rules produce. Not abstract adaptations, but actual organisms, each one a quiet solution to the problem of existing where light has never been part of the equation. There is a point, as the descent continues deeper into the Mariana Trench, where expectation quietly gives up. Not because something dramatic happens, but because nothing does. The environment is so extreme, so consistent in its pressure and darkness, that intuition begins to fail. By surface logic, life here should not work. There should be nothing capable of functioning under such weight, with so little energy, in a place so disconnected from sunlight and seasonal change. And yet, when cameras reach the bottom, something moves. The creatures that live at these depths do not look like variations of surface animals pushed a little further down. They look fundamentally reworked. They are not simply fish or crustaceans that have learned to tolerate pressure. They are organisms whose entire biology has been shaped by an environment that never relents. Their existence is not dramatic rebellion against nature. It is quiet compliance with it. One of the most frequently observed animals at trench depths is the amphipod. At the surface, amphipods are small, shrimp-like crustaceans, often overlooked, living in shallow waters, sand, or freshwater streams. In the Mariana Trench, their relatives grow larger and more robust, sometimes reaching sizes far beyond what surface versions ever achieve. These deep-sea amphipods move deliberately across the sediment, scavenging whatever organic matter arrives from above. Their success is not accidental. Amphipods are opportunists with flexible diets. They can process a wide range of organic material, including decaying plant matter, animal remains, and microbial films. At trench depths, this flexibility becomes an advantage. When a larger food source arrives, such as the carcass of a fish or whale that has sunk all the way down, amphipods can appear in large numbers, stripping it down efficiently before retreating back into the sediment. Their bodies are built for pressure. They lack large gas-filled spaces. Their exoskeletons are thin but flexible, distributing force rather than resisting it. Internally, their enzymes and cell structures function normally under pressures that would destroy most surface organisms at the molecular level. They do not resist the deep. They belong to it. Another group that challenges expectation is the sea cucumber. On the surface, sea cucumbers are slow-moving, soft-bodied animals often found on coral reefs or shallow seafloors. In the deep ocean, and even at trench depths, sea cucumbers take on new forms. Some develop elongated, almost translucent bodies. Others grow paddle-like appendages that allow them to lift slightly above the seafloor, drifting slowly as they feed. These deep-sea sea cucumbers consume sediment itself, extracting organic particles and microbes as it passes through their bodies. In an environment where food is scarce and dispersed, this strategy allows them to survive on what is always present, even if it is nutritionally poor. Their metabolism is slow. Their movements are minimal. They process the deep ocean floor the way earthworms process soil, quietly recycling material over long periods. Fish, perhaps the most surprising residents of the Mariana Trench, have drawn particular attention. For many years, scientists believed that vertebrate life could not exist beyond a certain depth, roughly 8,000 meters. The combination of pressure and biochemical constraints was thought to impose a hard limit. This assumption held until direct observation proved otherwise. At depths exceeding 8,000 meters, researchers have recorded the presence of snailfish. These fish do not resemble the sleek, muscular swimmers seen near the surface. They are pale, gelatinous, and delicate in appearance. Their bones are poorly ossified, their muscles soft. Their bodies are supported not by rigidity, but by the surrounding water itself. Snailfish lack swim bladders. Instead, they rely on high concentrations of osmolytes, small organic molecules that help stabilize proteins under pressure and maintain buoyancy. One of these compounds, trimethylamine N-oxide, plays a crucial role in allowing their enzymes to function normally at extreme depths. The deeper the fish lives, the higher the concentration of this compound in its tissues. This biochemical solution is elegant but limited. Beyond a certain depth, the concentration required to stabilize proteins would interfere with other cellular processes. This appears to set an upper limit on how deep fish can live. The snailfish observed near the bottom of the Mariana Trench represent life operating right at that boundary, balanced delicately between functionality and failure. Other vertebrates do not reach these depths. Sharks, whales, and most fish disappear thousands of meters above the trench floor. The snailfish is not an exception that breaks the rules. It defines where those rules end. Invertebrates, however, push further. Tiny foraminifera, single-celled organisms with shell-like structures, have been found in trench sediments. These organisms are not passive remnants drifting down from above. They are active residents, living, reproducing, and interacting with their environment. Some incorporate sediment particles into their shells, building structures suited to the pressure and chemistry of the deep. Microbial life, though invisible to the naked eye, may be the most abundant and resilient form of life at trench depths. Bacteria and archaea inhabit sediments, water, and even the tissues of other organisms. They break down organic material, recycle nutrients, and form the base of trench ecosystems. Some are adapted to high pressure through specialized membrane structures and enzyme systems. Others rely on slow metabolic pathways that minimize energy requirements. What is striking about these creatures is not their strangeness, but their restraint. They do not exhibit exaggerated features or extreme behaviors. There are no glowing predators lurking in the shadows at the trench floor. There are no massive forms dominating the environment. everything is scaled to scarcity. Size, speed, and complexity are limited by what the environment can support. This stands in contrast to popular depictions of the deep sea as a realm of monstrous proportions and constant danger. In reality, the deepest parts of the ocean are among the least aggressive environments on Earth. Predation occurs, but it is infrequent. Encounters are rare. Many organisms go long periods without interacting with others at all. The rarity of encounters shapes behaviour. Some deep-sea organisms exhibit sit-and-wait strategies, conserving energy until an opportunity arises. Others move continuously but slowly, covering large areas over time rather than quickly exploiting small patches. There is little competition in the traditional sense. Instead, survival depends on endurance and efficiency. Reproduction among trench organisms reflects this reality. Many species produce fewer offspring, investing more energy into each one. Eggs may be larger, containing more nutrients to support development in a food-poor environment. Larval stages, if they exist, may be brief or bypassed entirely. Some organisms brood their young, protecting them until they are capable of surviving independently. These strategies result in populations that change slowly. Genetic variation accumulates over long timescales. Evolution proceeds, but without the rapid bursts seen in more dynamic environments. This can give the impression that trench organisms are living fossils, unchanged remnants of ancient life. In reality, they are continually adapting, just along a slower trajectory shaped by stability rather than disruption. The idea that these creatures should not exist comes from applying surface expectations to a fundamentally different environment. From the perspective of the trench, their existence is not surprising. They are exactly what the conditions allow. They are not defying the environment, they are expressions of it. Human exploration has occasionally revealed how fragile this balance is. When submersibles arrive, lights flood the seafloor. Sediment is stirred, noise propagates through the water. For organisms adapted to near total darkness and silence, these disturbances are profound, even if temporary. Yet after the vehicles depart, the environment settles back into its baseline state. The creatures remain. There is a quiet lesson in this persistence. Life does not require comfort. It requires compatibility. Where conditions are harsh but stable, life can find a way to fit itself precisely into the available space. The Mariana Trench is not a place of constant struggle. It is a place of careful adjustment. As exploration continues, new species are still being discovered. Many are known only from a handful of specimens or brief video clips. Each one expands understanding of what biology can accommodate, not by expanding outward aggressively, but by narrowing inward, refining itself until nothing unnecessary remains. These creatures do not announce their presence. They do not challenge the environment or seek to escape it. They exist quietly at the bottom of the world, living proof that the limits humans imagine are often reflections of our own constraints, not those of life itself. With these organisms in mind, attention naturally shifts from the visible to the invisible, from bodies moving across sediment to the chemical processes that sustain them. The next layer of the trench is not defined by shape or motion, but by reactions occurring molecule by molecule, quietly determining what can exist in a place where almost everything is pressed to its limits. At the bottom of the Mariana Trench, chemistry stops being a background detail and becomes the environment itself. When light is gone, when temperature is fixed near freezing, and when pressure dominates every physical interaction, survival depends not on anatomy alone, but on reactions happening at scales far too small to see. Molecules determine what lives and what does not. Bonds form or fail. Proteins hold their shape or collapse. Energy moves through systems not as heat or light, but as slow, deliberate chemical exchanges. From the surface, it is tempting to think of chemistry as something that happens in laboratories or textbooks, governed by neat equations and controlled conditions. In the abyss, chemistry is not controlled. It is absolute. The pressure alone alters how atoms interact. Reactions that are stable at sea level behave differently under 1,000 atmospheres. Volumes shrink, solubility changes, reaction rates shift. Even the structure of water itself is subtly altered by compression. Water, the medium that defines life in the ocean, behaves differently under extreme pressure. Its density increases. The way it interacts with dissolved gases and ions changes. Oxygen remains present in deep water, but at lower concentrations than near the surface. This means organisms must extract it efficiently, often relying on specialized proteins that bind oxygen more readily than human hemoglobin ever could. Without this efficiency, respiration would fail long before energy shortages became an issue. Carbon, the backbone of life's chemistry, also takes on a different role. In surface ecosystems, carbon cycles rapidly through plants, animals, and the atmosphere. In the deep ocean, that cycle slows dramatically. Organic carbon arrives as sinking debris, fragmented and degraded. Microbes break it down further, releasing carbon dioxide back into the water. Some of that carbon becomes locked into sediments, buried for thousands or millions of years. The trench acts not just as a habitat, but as a carbon sink, quietly storing material removed from the active surface cycle. Nitrogen follows a similarly altered path. On land and in shallow seas, nitrogen cycles through plants, animals and bacteria, driven largely by biological demand and oxygen availability. In the abyss, nitrogen transformations are dominated by microbes adapted to low-energy conditions. Processes like denitrification and anammox convert nitrogen compounds slowly, releasing nitrogen gas back into the water column. These reactions do not make headlines, but they are essential. Without them, waste products would accumulate and life would stall. Sulfur chemistry becomes especially important in places where chemical energy replaces light as the foundation of the ecosystem. While the Mariana Trench is not dominated by hydrothermal vents, sulfur compounds still play a role. In sediments, bacteria reduce sulfate to sulfide, extracting energy in the process. This sulfide can then be used by other microbes, or react with metals, forming minerals that become part of the geological record. These reactions happen quietly, invisibly, but continuously. Methane is another key player. Produced by microbial activity deep within sediments, methane can seep upward into the water. In some environments, it fuels chemosynthetic communities. In others, it is consumed by specialized microbes before it ever reaches the surface. This microbial consumption acts as a biological filter, preventing large amounts of methane, a potent greenhouse gas, from escaping into the atmosphere. Even at the bottom of the trench, chemistry is linked to global systems. Pressure influences these chemical processes in subtle but profound ways. Reaction rates can slow or accelerate depending on how pressure affects molecular collisions. Some reactions that are unfavorable at low pressure become possible under compression. Others become less efficient. Enzymes, which catalyze biological reactions, must be precisely tuned to function under these conditions. A slight mismatch in structure can render an enzyme useless. This is why deep-sea organisms invest so heavily in molecular stability. Proteins are reinforced with chemical bonds that resist unfolding. Membranes are adjusted to maintain permeability without leaking. Small molecules called osmolytes accumulate inside cells, stabilizing proteins against pressure-induced distortion. These osmolytes do not provide energy. They provide resilience. Without them, the chemistry of life would fall apart. One of the most important osmolytes in deep-sea fish is trimethylamine N-oxide. This compound counteracts the destabilizing effects of pressure on proteins. As depth increases, so does the concentration of this molecule in the tissues of fish. This relationship is so consistent that it effectively sets a depth limit for vertebrate life. Beyond a certain point, the concentration required becomes incompatible with other cellular processes. Chemistry draws a line, and biology follows it. Microbial life operates under a different set of constraints. Bacteria and archaea have simpler structures and more flexible metabolic pathways. Many can survive at pressures that would destroy complex multicellular organisms. Some deep-sea microbes are pisophiles, organisms that not only tolerate high pressure, but require it to function normally. When brought to the surface, these microbes may die, not from the pressure change itself, but because their chemistry no longer works without compression. These microbes drive much of the trench's chemistry. They decompose organic matter, recycle nutrients, and mediate redox reactions that keep the system in balance. Without them, the trench would accumulate waste and lose its capacity to support higher life forms. They are the unseen engineers of the abyss, maintaining conditions that allow everything else to exist. The sediment at the bottom of the trench is a chemical archive. Layer by layer, it records what has fallen from above and what has been transformed below. Organic carbon, trace metals, pollutants, and microplastics all settle here eventually. Chemical reactions within the sediment determine how long these materials remain accessible or how deeply they are buried. Some compounds are broken down quickly. Others persist, altered but not destroyed. Human influence has reached even this depth, carried not by direct presence but by chemistry. Persistent organic pollutants, heavy metals, and synthetic compounds have been detected in trench organisms and sediments. These substances sink slowly, transported by particles and currents, until they reach the deepest parts of the ocean. There, they enter chemical cycles that were never shaped to handle them. The effects are not always immediately visible. Concentrations may be low, impacts may be subtle, but in an environment where life operates near the edge of energetic feasibility, even small chemical disruptions can matter. Toxins can accumulate in organisms that have few opportunities to eliminate them. Slow metabolisms mean slow detoxification. Long lifespans mean prolonged exposure. Chemistry also governs how the trench responds to change. Temperature shifts at the surface propagate slowly downward, altering deep water chemistry over decades or centuries. Changes in oxygen concentration can ripple through microbial communities, shifting reaction pathways and nutrient availability. The trench may feel isolated, but it is chemically connected to the rest of the ocean, and by extension, the planet. One of the most striking aspects of abyssal chemistry is its patience. Reactions occur slowly, steadily, without urgency. There are no rapid blooms or crashes. The system absorbs change gradually, buffering it through dilution and time. This makes the trench resilient in some ways, but vulnerable in others. Once altered, it may take centuries to return to a previous state. From a human perspective, the chemistry of the abyss feels distant and abstract. Molecules moving, electrons shifting, bonds forming and breaking far below the reach of light or sound. But this chemistry is what makes the existence of trench life possible. Without it, pressure and darkness would be insurmountable barriers. With it, life finds narrow pathways through extreme conditions. There is also something humbling in realizing that at the deepest point on Earth, existence is governed not by spectacle, but by balance. No grand displays, no sudden transformations, just chemistry doing what it has always done, under conditions that strip it down to its essentials. As attention continues forward, the focus begins to shift again, from reactions and molecules to the sensory world shaped by them. Chemistry sets the stage, but experience, however limited, still emerges. Even in the abyss, sound travels, vibrations propagate, and the deep ocean listens in its own way. At first glance, the deepest parts of the ocean seem silent in the most complete sense imaginable. There is no wind moving across the surface, no rain striking water, no waves breaking, no voices, engines, or familiar rhythms of human activity. Light is absent, movement is slow, and the environment appears almost suspended. It is tempting to imagine the bottom of the Mariana Trench as a place of total quiet, a void where nothing disturbs the stillness. But the deep ocean is not silent. It simply speaks in a language that is unfamiliar and easy to overlook. Sound behaves very differently in water than it does in air. Water is denser, more elastic, and far more efficient at transmitting acoustic energy. A sound that would fade quickly in the open air can travel vast distances underwater, especially at low frequencies. In the deep ocean, sound can move for hundreds or even thousands of kilometers with relatively little loss of energy. This makes sound not just a sense, but a defining feature of the environment. At trench depths, sound replaces sight as the primary medium through which information moves. Darkness eliminates visual cues, but sound continues uninterrupted. Every movement, impact, or vibration produces a signal that spreads outward, bending with layers of temperature and pressure, reflecting off seafloor contours and persisting long after its source has stopped. The deep ocean soundscape is not loud in the way a city or storm is loud. It is subtle, layered, and dominated by low frequencies. These sounds are often below the range of human hearing, or so faint that they require sensitive instruments to detect. Yet for organisms adapted to this environment, these vibrations are meaningful. They carry information about distance, movement, and change. One of the most constant sources of sound in the deep ocean is geological activity. The Earth is not still beneath the trench. Tectonic plates shift. Stress builds and releases. Small earthquakes occur deep within the subducting slab. These events generate vibrations that travel through rock and water alike. At the bottom of the trench, such sounds may arrive as distant rumbles or subtle tremors, barely perceptible but persistent over geological time. Another contributor is the movement of water itself. Deep ocean currents are slow, but they are not absent. As water masses slide past one another, interact with seafloor features, or descend along slopes, they generate low-level noise. This sound is continuous, forming a kind of acoustic background that never fully stops. It does not announce itself, it simply exists. Biological sound is present as well, though it is sparse compared to shallower regions. Many deep-sea organisms do not produce sound deliberately. There is little reason to advertise presence in an environment where encounters are rare and energy is precious. Instead, sound arises incidentally. The movement of a crustacean across sediment, the closing of a jaw, the flutter of fins, these small actions create vibrations that travel farther than their creators might intend. Some animals, particularly larger species in the mid-water zones above the trench, actively use sound to communicate or navigate. Whales, for example, produce powerful low-frequency calls that can travel across entire ocean basins. These sounds do not stop at the trench walls. They pass over and through them, reaching depths far below where the whales themselves will ever go. At the bottom of the Mariana Trench, echoes of distant whales may still be present, stretched, distorted, and transformed by the journey. For trench-dwelling organisms, these distant sounds are part of the environment. They are not signals meant for them, but they are nonetheless detectable. Whether these sounds influence behaviour is still largely unknown. The deep ocean remains difficult to study acoustically at such depths, and much of what happens there is inferred rather than directly observed. The structure of the ocean itself shapes how sound moves. Layers of water with different temperatures and salinities bend sound waves, creating channels that trap and guide them. One such feature, the SOFAR channel, allows sound to travel enormous distances with minimal loss. While this channel lies above the trench, its effects can still influence the acoustic environment below, directing certain frequencies downward while dispersing others. In this way, the deep ocean becomes an archive of sound. Signals generated far away can arrive long after their source has changed or disappeared. A storm thousands of kilometers distant, a ship passing over a distant ridge, ice breaking in polar regions. These sounds can propagate through the ocean and reach depths that never experience the events themselves. Human activity has added a new layer to this soundscape. Ships, submarines, sonar systems, and industrial operations generate noise that travels far beyond their immediate location. Even though the Mariana Trench feels remote, it is not acoustically isolated. Low-frequency noise from shipping lanes and naval exercises can reach deep waters, introducing sounds that were absent for most of the ocean's history. The impact of this noise on deep-sea life is not fully understood. Many trench organisms have limited sensory ranges and may not respond strongly to distant or unfamiliar sounds. Others may be sensitive to vibration in ways that are not yet well documented. Because life at depth operates with narrow energy margins, even small disruptions could matter, especially if they are chronic rather than occasional. Silence in the deep ocean is therefore relative. There are no sudden crashes or sharp noises most of the time, but there is also no complete absence of sound. Instead, there is a low-level acoustic presence that forms part of the background conditions of life. For organisms adapted to this environment, this is normal. It does not demand attention. It does not signal danger or opportunity unless it changes. When human explorers descend in submersibles, they introduce a dramatic acoustic disturbance. Thrusters hum. Metal creaks under pressure. Equipment vibrates. These sounds are loud and abrupt compared to the baseline quiet of the trench. For a brief time, the soundscape changes. Organisms may retreat, freeze, or alter their behavior. Then, when the vehicle departs, the sound fades, and the environment returns to its prior state. This temporary disturbance highlights how stable the deep ocean normally is. Unlike surface environments, where noise is constant and varied, the trench soundscape is relatively predictable. Changes are infrequent. When they do occur, they often signal something significant, a seismic event, a large object falling, or a rare biological interaction. There is also a psychological dimension to deep ocean sound, particularly for the humans who descend there. Inside a submersible, surrounded by thousands of meters of water, sound becomes intimate. Every creak of the hull is amplified by awareness. Every unfamiliar noise invites interpretation. Is that the structure adjusting? A piece of equipment shifting? Something outside brushing against the hull? In an environment where visual confirmation is limited, sound carries emotional weight. For the trench itself, however, sound is simply another physical phenomenon. It travels, reflects, dissipates, and fades according to rules that do not change. The ocean does not react to being heard or not heard. It does not notice when humans listen. The soundscape exists whether it is interpreted or ignored. The idea of silence at the bottom of the world is appealing because it suggests peace, finality, and separation from surface chaos. In reality, the deep ocean is quieter than most places humans inhabit, but it is not empty. It is filled with subtle signals that reflect the ongoing processes of the planet. Tectonics, circulation, distant life, and human activity all leave their acoustic traces. Understanding this soundscape adds another layer to understanding what exists at the bottom of the Mariana Trench. It is not just a physical space defined by pressure and darkness. It is also an environment shaped by vibration and resonance, by the slow transmission of energy through water and rock. As focus continues to narrow, attention begins to shift from the natural sounds of the trench to something more unexpected. Not vibrations generated by geology or biology, but the faint, unmistakable traces of human presence that have reached even this depth, carried not by intention, but by gravity and time. The idea that the deepest place on Earth could remain untouched once felt reasonable. For most of human history, the Mariana Trench was not only unreachable but unknowable. It existed beyond maps, beyond stories grounded in evidence, beyond any practical influence from the surface world. Even after the first measurements hinted at its extreme depth, it still seemed safely isolated. Too far down, too hostile, too remote for human activity to matter. And yet, isolation in the ocean is never complete. Gravity, currents, and time are remarkably effective carriers. Human traces at the bottom of the world did not arrive there through exploration or intention. They arrived slowly, quietly, and unintentionally, sinking through layers of water that once felt like a sufficient barrier. What rests at the trench floor today is not the result of presence, but of reach. One of the earliest and most striking discoveries made during deep-sea expeditions was debris. Not large objects at first, but fragments, fibres, particles, materials that had no business being there. Plastic bags, food wrappers, bits of packaging, synthetic fibres from clothing, all found thousands of meters below the surface. At first, these discoveries seemed like anomalies, perhaps carried by unusual currents or rare events. Over time, it became clear they were not exceptions, they were signals. Plastic, in particular, has proven to be an extraordinarily persistent traveller, lightweight enough to float for years, durable enough to resist degradation, and abundant enough to saturate the ocean. Plastic eventually breaks down into smaller and smaller pieces. These microplastics do not disappear. They become suspended in the water column, hitching rides on sinking organic particles or aggregating into denser clusters that descend slowly but steadily. By the time these particles reach the Mariana Trench, they are often unrecognisable as objects. They exist as fragments embedded in sediment, mixed with natural material, indistinguishable to the naked eye. But chemically they remain synthetic. They do not belong to the system that surrounds them. Researchers sampling trench sediments have repeatedly found microplastics present in measurable quantities. These particles are not inert. They can absorb toxins, concentrate pollutants, and interact with biological tissues. When ingested by deep-sea organisms, they enter food webs that were never shaped to process synthetic material. Even more unsettling is the discovery of persistent organic pollutants in trench life. Chemicals such as polychlorinated biphenyls, banned decades ago in many countries, have been detected in amphipods and other trench organisms. These compounds were released at the surface, dispersed globally through air and water, and eventually settled into the deepest parts of the ocean. The trench, far from being a pristine refuge, has become a sink for the byproducts of industrial activity. Heavy metals tell a similar story. Mercury, lead, and other elements released through mining, combustion, and manufacturing bind to particles and sink. Over time, they accumulate in sediments and organisms. In the trench, where life processes material slowly and elimination pathways are limited, these substances can persist and concentrate. The effects are difficult to observe directly, but their presence alone is evidence of connection. Even sound, though intangible, leaves a trace. The deep ocean carries the acoustic imprint of human activity. Shipping traffic, sonar, and industrial noise propagate through water and reach depths once thought acoustically isolated. These sounds may not leave physical debris, but they alter the sensory environment, introducing signals that did not exist before. There are also more literal human artifacts. During one of the few descents to the trench floor, a plastic bag was observed resting on the sediment. Not a fragment, not a fibre, but an intact object, recognisable and out of place. It had drifted down from the surface, settling into a landscape that had evolved without any concept of waste. This moment did not provoke outrage or spectacle. It provoked something quieter, a realization that there is no edge to human influence that can be relied upon to stop it. If gravity can carry debris to the deepest point on Earth, then remoteness is not protection. It is important to note that the trench is not littered. It is not a dumping ground in the way coastal waters or surface gyres can be. Human traces are sparse, scattered, diluted by depth and time, but scarcity does not mean absence. In an environment defined by low input and slow change, even rare intrusions matter. The presence of human-made materials at trench depths also reveals something about how the ocean functions as a system. The deep sea is not separate from the surface, it is downstream from it. Everything that enters the ocean eventually begins a slow descent, broken down, transformed, redistributed. The trench is the end point of that process, where what remains finally comes to rest. This makes the Mariana Trench a kind of archive, not just of geological history or biological adaptation, but of human activity. Sediment layers capture changes in surface production, pollution, and climate over time. Chemical signatures preserved at depth tell stories about what happened far above, sometimes decades earlier. Climate change, though not directly visible at the trench floor, also leaves a chemical imprint. Warming surface waters alter circulation patterns, changing how oxygen and nutrients are delivered to depth. Ocean acidification affects carbonate chemistry, influencing how shells and sediments form. These changes propagate slowly, but they propagate nonetheless. The deep ocean responds on timescales that do not align with political cycles or news coverage. There is a temptation to view these human traces as evidence of damage, and in many ways they are. But they also function as proof of connection. The trench is not a separate world. It is part of the same planet, governed by the same flows of matter and energy. The idea that something can be thrown away loses meaning when there is no true away. For the organisms living at the bottom of the trench, human traces are not symbolic. They are physical realities encountered without context. A microplastic particle is not recognized as foreign. It is simply another object, another surface, another potential hazard or carrier of chemicals. The organisms respond not with judgment, but with biology. Because life at depth operates slowly, the long-term effects of these intrusions remain uncertain. Some organisms may tolerate them, others may suffer subtle impairments that accumulate over generations. The trench does not offer quick feedback. Changes are recorded gradually, their consequences unfolding over decades or centuries. What makes this particularly striking is the contrast between human presence and human absence. At the surface, influence is immediate and visible. At the trench floor, it is delayed, indirect, and easy to ignore. Yet it arrives all the same. There is no evidence that trench ecosystems are collapsing or failing. They continue to function much as they always have, but the assumption that they are untouched is no longer accurate. The deepest point on Earth now carries a faint but unmistakable imprint of surface civilization. This realization does not demand panic or despair. It demands perspective. The Mariana Trench is resilient in certain ways, its stability buffers it against sudden change. But resilience does not mean invulnerability. It means change is absorbed slowly, sometimes invisibly, until it is not. As attention continues forward, the question shifts again. Not just what exists at the bottom of the trench, but what condition it is in. Whether this extreme environment, shaped by patience and balance, is remaining intact or beginning to drift under pressures it did not evolve to handle. The next layer of understanding lies not in individual traces, but in the overall health of the deep. The question of whether the Mariana Trench is alive or slowly dying sounds dramatic at first, as though the deep ocean might be teetering on the edge of some visible collapse. In reality, nothing at the bottom of the trench announces its condition in such clear terms. There are no sudden die-offs, no bleaching events that turn an ecosystem visibly pale, no mass movements that signal immediate distress. The trench does not fail loudly. If it changes, it does so quietly, over spans of time that are difficult to witness in a single lifetime. To ask whether the trench is alive or dying is really to ask how life behaves in a place where stability has always been the defining feature. The deep ocean was never abundant in the way surface ecosystems are. It was never fast, noisy, or productive by human standards. Life there has always existed close to the minimum energy required to persist. That makes the question more subtle. A system that has never flourished in obvious ways cannot decline in obvious ways either. Life in the Mariana Trench continues to exist, Organisms still move across the sediment. Microbes still process organic material. Amphipods still scavenge. Snailfish still patrol the upper reaches of Hadal depth. In that sense, the trench is very much alive. There is no evidence of a sudden collapse or an abrupt loss of biodiversity. But life existing is not the same as life thriving, and thriving is not the same as remaining unchanged. The deep ocean is often described as stable, but stability does not mean static. It means change happens slowly. The trench responds to surface events with delay, sometimes decades or centuries after the initial cause. This time lag can create the illusion of immunity, when in reality the system is simply processing information at a different speed. One of the clearest indicators of change is chemistry. Deep water chemistry reflects conditions at the surface, but with a long delay. Oxygen levels in the deep ocean are determined by how surface waters absorb oxygen from the atmosphere and then sink. Changes in temperature, circulation, and productivity at the surface eventually alter how much oxygen reaches depth. In some regions of the deep ocean, oxygen concentrations have already begun to decline. At trench depths, oxygen is present but limited. Organisms are adapted to low concentrations, but there are still thresholds below which even these adaptations fail. A slow decline in oxygen does not cause immediate death. It causes gradual stress. Metabolisms become less efficient. Growth slows further. Reproduction becomes more difficult. These effects are hard to observe without long-term monitoring, which is rare at such depths. Temperature change is another factor. The deep ocean warms very slowly compared to the surface, but it does warm. Even a fraction of a degree can matter in an environment where biological processes are finely tuned to narrow ranges. Warmer water holds less dissolved oxygen. It also alters chemical reaction rates. These shifts do not trigger alarms, but they quietly reshape the conditions under which life operates. Food supply is perhaps the most critical variable. The trench depends on material sinking from above. Changes in surface productivity, driven by climate shifts, nutrient availability, and human activity, influence how much organic matter reaches depth. If surface ecosystems produce less biomass, less material sinks. If sinking particles are broken down more efficiently in mid-water zones due to warming or microbial changes, even less reaches the bottom. This creates a compounding effect. Less food arriving at the trench floor means organisms must stretch their already minimal energy budgets even further. Some may adapt by slowing growth or reproduction. Others may fail to reproduce successfully. Over long periods, this can lead to population declines that are difficult to detect because baseline numbers were low to begin with. Pollution adds another layer of complexity. Persistent organic pollutants and heavy metals have been detected in trench organisms. These substances do not arrive in concentrations high enough to cause immediate mortality. Instead, they accumulate slowly. In organisms with long lifespans and slow metabolisms, accumulation matters. Toxins can interfere with reproduction, development, and immune function. The effects may only become apparent after multiple generations. Microplastics, now found even in trench sediments, introduce physical and chemical stresses that did not exist before. They can act as vectors for pollutants, provide surfaces for microbial growth, and interfere with feeding processes. Again, the impact is not catastrophic in the short term, it is incremental. Noise pollution, though less studied at these depths, may also play a role. Chronic low-frequency noise from human activity alters the acoustic environment. For organisms that rely on vibration and sound to detect movement or locate food, this background noise could mask important signals. Whether this effect is significant at trench depths remains uncertain, but uncertainty itself is part of the picture. It is also important to consider resilience. Life in the trench has survived enormous changes in Earth's history. Plate movements, shifts in ocean circulation, mass extinctions at the surface, all occurred while deep-sea ecosystems persisted. This resilience is real. It is grounded in the stability of the environment and the slow pace of life. However, past changes unfolded over geological timescales. Current changes are happening faster, driven by human activity rather than tectonics or orbital cycles. The deep ocean may still buffer these changes, but buffering does not eliminate impact, it delays it. There is also the question of recovery. If a surface ecosystem is damaged, recovery can be visible within years or decades if conditions improve. In the trench, recovery may take centuries. If a population declines significantly, recolonization is slow, larval dispersal is limited, growth is slow, reproduction is infrequent. Once lost, certain lineages may not return within any meaningful human time frame. This makes the trench vulnerable in a specific way, not because it is fragile in the sense of easily broken, but because it is slow to heal. Disturbances accumulate quietly, and their effects persist long after the initial cause has passed. Yet it would be inaccurate to describe the trench as dying. That word implies a trajectory toward absence, toward lifelessness. There is no evidence that the Mariana Trench is on such a path. Life continues, processes continue, the system remains functional. A more accurate description is that the trench is changing. It is responding, slowly and subtly, to a world above that is changing more rapidly than it ever has before. Whether those changes will push the system beyond its adaptive capacity remains unknown. The challenge in answering this question lies in the limits of observation. Long-term data from the trench are scarce. Expeditions are rare. Monitoring equipment is expensive and difficult to maintain at such depths. Without continuous records, distinguishing natural variability from long-term trends is difficult. What is clear is that the trench is not isolated. It is connected chemically, physically and biologically to the rest of the ocean. Changes at the surface do not stop at the thermocline or the abyssal plain. They propagate downward, delayed but persistent. There is also a philosophical aspect to the question. Humans tend to measure life by productivity, abundance and visibility. By those standards, the trench was never particularly alive to begin with, but life is not defined by excess. It is defined by persistence. The Mariana Trench represents one of the most persistent forms of life on Earth. Not because it is ancient in a static sense, but because it has learned to exist within extreme constraints without exhausting its environment. It does not overshoot. It does not boom and bust. It exists within limits. That may be its greatest vulnerability and its greatest strength. Vulnerable to cumulative, subtle change. Strong in its capacity to endure slow shifts without collapse. So is the trench alive or slowly dying? The most honest answer is that it is alive and changing, not dying in the dramatic sense, but not untouched either. It exists in a state of quiet adjustment, absorbing signals from the surface world at a pace that feels almost geological. Understanding this challenges simple narratives. There is no single moment where the trench tips from healthy to unhealthy. There is no clear threshold that marks the beginning of decline. Instead, there is a gradient of change, unfolding beneath the surface, largely invisible but no less real. As attention continues forward, the focus begins to widen again, from the condition of the trench itself to what it represents. What this extreme environment, balanced between endurance and vulnerability, reveals about the planet as a whole, and about humanity's place within systems that move more slowly than our own sense of time. Standing at the surface of the Earth, it is easy to believe that the planet reveals itself willingly. Mountains rise into view, rivers trace their paths across land, storms announce their arrival with sound and motion. Most of what humans understand about Earth has been learned by looking outward, at features that are visible, accessible and responsive to observation. The deep ocean, and especially the Mariana Trench, teaches a different lesson. It shows that some of the most important truths about the planet exist far beyond easy reach, operating quietly and patiently beneath layers of distance and time. The first thing the deep teaches us is scale. Not the kind of scale measured only in kilometers or meters, but the kind that reshapes perspective. The surface of the Earth feels expansive when crossed on foot or viewed from an airplane. Continents seem vast, oceans appear endless, yet the Mariana Trench reveals that much of the planet's true dimension lies vertically, not horizontally. The Earth is not just wide, it is deep in a way that changes how processes unfold and how influence spreads. This vertical scale alters how energy moves through the system. Sunlight powers the surface, but its influence fades quickly with depth. Below that, gravity takes over, pulling material downward in a slow, continuous rain. The trench shows that Earth is organised not only by light and atmosphere, but by sinking, settling and accumulation. What happens at the surface does not vanish. It migrates downward, transformed but persistent. The deep also teaches patience. Geological processes that shape the trench occur over millions of years. Tectonic plates drift, collide, and subduct at rates too slow to notice without instruments and long records. Sediments accumulate grain by grain. Chemical signatures build layer upon layer. Nothing happens quickly, but nothing stops happening either. The Earth beneath the ocean is not dormant, it is methodical. This patience extends to biological systems as well. Life in the trench evolves slowly, responding to stable conditions rather than constant disruption. The deep teaches that evolution does not always reward speed or adaptability in the short term. Sometimes it rewards consistency, efficiency, and restraint. Traits that would be liabilities in dynamic surface environments become strengths in the deep. Another lesson lies in interconnectedness. The trench feels isolated, but it is not separate. Its chemistry reflects surface conditions. Its food supply depends on productivity far above. Its temperature and oxygen levels are shaped by global circulation patterns. The deep ocean is downstream from everything else. This challenges the idea that environments can be neatly divided into independent zones. On Earth, separation is often an illusion created by distance rather than reality. This interconnectedness also reveals how influence accumulates. Small changes at the surface, repeated over time, can alter conditions at depth. A slight shift in temperature, a change in nutrient flow, a new chemical introduced into the system, each on its own may seem insignificant. Together, over decades or centuries, they reshape environments that feel remote and protected. The deep teaches humility in the face of limits. For all of human ingenuity, access to the deepest parts of the planet remains rare and constrained. We rely on machines, careful planning, and narrow margins of safety to observe environments that exist effortlessly without us. The trench does not yield its secrets easily, and when it does, it offers them without regard for human expectations. This humility extends to understanding. The deep ocean reminds us that knowledge is always incomplete. Even now, much of the trench remains unexplored. Many species have been observed only once or twice. Long-term trends are inferred rather than measured directly. The Earth contains systems that operate beyond the resolution of our current tools, and acknowledging that limitation is part of understanding the planet honestly. There is also a lesson about resilience and vulnerability coexisting. The deep ocean has persisted through mass extinctions, climate shifts, and tectonic reorganizations. It is resilient in the sense that it does not collapse easily. But that resilience is paired with fragility of a different kind. Because change happens slowly, recovery also happens slowly. Disturbances linger, effects accumulate. This dual nature challenges simple narratives about environmental protection. The trench does not need saving in the dramatic sense. It does not require immediate intervention to prevent collapse, but it does require consideration. Its slow pace means that mistakes are not quickly corrected. Actions taken at the surface today may echo quietly at depth, long after their origin is forgotten. The deep also teaches that Earth is not designed for human convenience. The conditions at the bottom of the Mariana Trench are not hostile in a moral sense. They are simply incompatible with human biology. This distinction matters. It reminds us that the planet does not exist to accommodate us. We exist within it, adapted to a narrow range of conditions that happen to align with our needs. Recognizing this can shift how we think about habitability. Earth is often described as uniquely suited for life, but the trench shows that life does not require comfort or familiarity. It requires consistency and opportunity. Even environments that feel extreme from a human perspective can support complex systems if the rules remain stable. The trench also reframes time. At the surface, time is marked by days, seasons, and years. In the deep, these markers lose meaning. Change is measured in sediment layers and chemical gradients. This difference highlights how human time is only one way of experiencing the planet. Earth operates on multiple clocks simultaneously, some ticking far more slowly than others. Understanding this can alter how responsibility is perceived. When consequences unfold slowly, accountability becomes abstract. It is easy to assume that what cannot be seen cannot be affected. The deep ocean contradicts this assumption. It absorbs, records, and responds, even if the response arrives long after the cause. There is also a lesson in restraint. Life in the trench does not overproduce. It does not expand aggressively. It exists within limits imposed by energy availability. This stands in contrast to many surface systems, including human societies, which often push against limits until they are enforced by failure. The deep suggests an alternative model, one where persistence is achieved through balance rather than growth. The Earth beneath the ocean is not dramatic in the way surface landscapes can be. There are no sweeping vistas or rapid transformations. Its drama lies in continuity, in the fact that processes set in motion millions of years ago continue without interruption. The trench is a reminder that the planet's most enduring features are not always its most visible. Perhaps the most profound lesson the deep teaches is that Earth is not fully known and may never be. Even with satellites, sensors, and sophisticated models, vast portions of the planet remain largely unobserved. This is not a failure of science. It is a reflection of the planet's complexity and scale. The Mariana Trench exists not as a challenge to be conquered, but as a context to be understood. It shows that Earth is layered, patient, interconnected, and indifferent to human narratives. It reminds us that what feels distant is often deeply connected, and what feels stable may be quietly changing. As attention continues to move forward, the focus shifts again from what the deep reveals about the planet to what it reveals about those who study it. Not in terms of achievement or exploration, but in terms of perspective. The trench does not just reflect Earth back to us. It reflects ourselves, our assumptions, our limits, and our place within a system far larger and slower than our own rhythms. Looking into the deepest parts of the ocean is often described as an act of exploration, but what it really becomes, almost inevitably, is an act of reflection. The Mariana Trench does not mirror human features or emotions in any obvious way. It offers no faces, no gestures, no familiar expressions, and yet the longer attention lingers there, the more it begins to expose the assumptions humans carry about themselves. Not through confrontation, but through contrast. Humans are a species shaped by surfaces. We evolved under open skies, oriented by light, weather, and landmarks that change from day to day. Our sense of time is built around cycles we can see and feel. Our sense of safety is tied to visibility, control, and predictability. The deep ocean strips these away without hostility or intention. It simply exists without accommodating them. In doing so, it quietly reveals how narrow the conditions are under which humans feel at home. One of the first things the deep teaches us is how dependent we are on immediacy. Human perception favours fast feedback. We expect actions to have visible results. Effort should lead to change. Cause should follow effect within a time frame we can register. The trench does not operate that way. Processes unfold slowly. Signals propagate with delay. Consequences accumulate invisibly. This difference can feel unsettling, not because the system is broken, but because it refuses to perform on human schedules. This impatience shapes how humans evaluate success and failure. At the surface, productivity is often measured by speed, output, and growth. More is better. Faster is preferable. In the trench, these metrics collapse. Life persists not by producing more, but by using less. Survival is not about expansion, but about fitting precisely within constraints. The deep does not reward ambition. It rewards alignment. That contrast highlights a deeper discomfort. Humans tend to define progress as movement outward, upward, or forward, expansion of territory, accumulation of resources, acceleration of processes. The deep ocean suggests that endurance can be achieved without any of these. It presents a model of existence that does not strive to overcome its environment, but to exist within it indefinitely. This does not make the trench morally superior or instructive in a prescriptive sense. It simply shows that human definitions of success are not universal. They are local solutions to local conditions. The discomfort arises when those solutions are mistaken for absolutes. The trench also exposes the human need for narrative. Humans understand the world through stories, beginnings, climaxes, endings, heroes and obstacles, progress and resolution. The deep ocean resists narrative structure. There is no climax at the bottom of the trench, no final revelation, no turning point where understanding suddenly arrives. What exists there is repetition, stability, and gradual change. This resistance can feel unsatisfying. It challenges the expectation that knowledge should arrive as insight or discovery. Instead, understanding the deep requires patience, accumulation, and acceptance of partial information. It requires comfort with not knowing everything, and with the possibility that some systems are not designed to be fully understood from a human perspective. In this way, the trench becomes a test of humility. Not humility as self-diminishment, but as accurate self-assessment. Humans are capable of remarkable feats. They can build machines that survive pressures once thought impossible. They can send sensors into darkness and retrieve data from the edge of physical limits, but they cannot inhabit the deep. They cannot adapt biologically to its conditions. Their presence there is temporary, mediated, and fragile. This fragility is often hidden by technology. Thick hulls, redundant systems, precise engineering create an illusion of control, but every descent into the trench carries risk. Every successful return depends on materials behaving exactly as designed. The margin for error is narrow. The environment does not forgive mistakes. Recognizing this fragility can be uncomfortable, especially for a species accustomed to reshaping environments to suit its needs. The deep ocean cannot be reshaped at scale. It cannot be drained, terraformed, or stabilized for permanent human presence. It exists beyond the reach of adaptation strategies that work elsewhere. This limitation is not a failure of ingenuity. It is a boundary condition. Boundaries are difficult for humans to accept. There is a tendency to treat every boundary as a temporary obstacle, something to be overcome with better tools or more effort. The trench suggests that some boundaries are not challenges, but facts. They define where one mode of existence ends and another begins. Another lesson the deep teaches is how easily humans mistake visibility for importance. Surface phenomena dominate attention because they are seen, felt, and experienced directly. Storms, fires, floods, and heat waves provoke immediate response. The deep ocean changes quietly. Its signals are subtle. Its shifts are measured in fractions and trends rather than events. This mismatch can distort priorities. What is visible feels urgent. What is invisible feels distant. Yet the trench demonstrates that invisibility does not equate to irrelevance. Some of the most consequential processes on Earth occur far from view, unfolding slowly, shaping conditions long before their effects are noticed elsewhere. The deep also reflects how humans conceptualize value. Things are often valued based on utility, accessibility, or potential for use. The Mariana Trench offers little in these terms. It is difficult to access. It provides no immediate resources. It does not support infrastructure or settlement. By conventional standards, it appears useless, and yet its value lies precisely in what it reveals. It provides insight into planetary processes, biological limits, and chemical resilience. It functions as a record of Earth's history and a buffer in global cycles. Its worth is not extractive, it is contextual. This challenges a deeply ingrained assumption that value must be tied to use. The trench exists without being used, and in doing so, it exposes how narrow utilitarian frameworks can be. Not everything meaningful must be optimized or exploited. Some things matter because they exist as they are. There is also a lesson about responsibility embedded in the deep. Human traces have reached the trench not through intention, but through consequence. Plastics, pollutants, and chemical signatures sink, carried by gravity and time. The trench receives them without consent or defense. This reveals something uncomfortable about human influence. It is often diffuse, delayed, and disconnected from awareness. Actions taken in one place manifest consequences elsewhere, long after the original context has faded. Responsibility becomes abstract, stretched across space and time. The deep ocean does not accuse or judge, it simply records. Sediments layer quietly. Organisms incorporate what arrives. Chemistry adjusts. The lack of immediate feedback does not mean absence of impact. It means impact unfolds on a timeline that does not align with human attention spans. Recognizing this can shift how responsibility is understood. It is not always about preventing immediate harm. It is about acknowledging that systems absorb change even when that change is not immediately apparent. The trench teaches that distance does not equal separation, and delay does not equal disappearance. The deep also offers insight into human curiosity. Despite the absence of practical benefit, people have been drawn to explore the trench. Not for profit, not for settlement, but for understanding. This curiosity is one of humanity's defining traits. It drives exploration beyond immediate need, motivated by a desire to know rather than to use. At the same time, the trench tempers that curiosity. It does not reward haste. It does not yield easily. It demands careful planning, restraint, and respect for limits. Curiosity alone is not enough. It must be paired with humility and patience. There is also a quieter lesson about presence. Human visits to the trench are brief. Submersibles descend, observe, and leave. The environment barely registers the interruption. Life continues as before. This contrast highlights how small human presence is relative to the scale of the planet. This does not diminish human significance. It contextualizes it. Humans are not the center of Earth's processes. They are participants within them. The deep ocean makes this difficult to ignore. It exists entirely outside human narratives, yet remains connected to them. The trench also reframes the idea of isolation. From a human perspective, the bottom of the Mariana Trench feels utterly alone. No communication, no contact, no immediate connection to the surface. But biologically and chemically, it is not isolated. It is part of continuous flows of matter and energy. This suggests that isolation is often a matter of perception rather than reality. What feels distant may be deeply connected through pathways that operate beyond direct awareness. Humans tend to equate connection with proximity. The deep reveals that connection can persist without closeness. Another reflection emerges around control. Humans often seek to manage environments, to stabilize systems, to predict outcomes. The trench resists management. Its conditions are too extreme, its processes too slow, its scale too vast. Control is replaced by observation. This shift can be unsettling, but it also offers relief. Not every system must be managed. Some can be understood, respected, and left largely alone. The deep ocean suggests that coexistence does not always require intervention. Finally, the trench teaches something about perspective. Human lives are short relative to geological time. Societies rise and fall faster than deep ocean processes register. This disparity can make individual actions feel insignificant, but the trench also shows that accumulation matters. Small inputs, repeated over time, shape even the most remote environments. This duality can reframe agency. Individual moments may be brief, but patterns persist. Choices made repeatedly become forces. The deep ocean does not respond to single actions. It responds to trends. In this way, the trench reflects humanity back to itself, not as conqueror or destroyer, but as participant, a species capable of remarkable insight and unintended consequence. Curious, inventive, impatient, and often unaware of how far its influence travels. The deep does not offer judgment or guidance. It offers context. It shows what exists when comfort is removed, when speed is irrelevant, when existence is stripped to essentials. In doing so, it reveals how much of human behaviour is shaped by conditions rather than absolutes. As attention continues forward, this reflection begins to broaden, from understanding ourselves in contrast to the deep, to understanding how this knowledge fits into the larger story. Not an ending, but a gentle widening of focus, carrying these lessons back toward the surface, where light returns, time accelerates, and the deep continues its quiet work far below. The ascent from the deepest place on Earth is never sudden. There is no dramatic release, no sharp boundary where the deep ends and the familiar begins. Rising from the bottom of the Mariana Trench is a slow unwinding, a gradual loosening of pressure, darkness, and stillness that does not disappear all at once but thins layer by layer. What changes first is not the environment itself but awareness, the sense that the deep has done what it needed to do, and will continue doing it long after attention shifts away. As depth decreases, pressure eases incrementally, not in a way that can be felt moment to moment, but in a way that reshapes possibility. Materials that could not survive below begin to make sense again. Biological limits soften. The rules that governed every reaction at the bottom loosen their grip. Nothing vanishes. It simply becomes less absolute. Darkness remains for a long time. Even as the ascent continues, light does not immediately return. There is a long stretch where the environment feels unchanged, where the absence of sunlight persists and the deep still feels dominant. This is a reminder that the surface world is thinner than it feels, a narrow band of brightness resting atop an enormous volume of shadowed water. Eventually, faint traces of light begin to appear. Not illumination, but suggestion. A barely perceptible shift in tone. A gradient rather than a glow. This return is subtle enough that it can be missed if not expected. Light does not announce itself. It resumes quietly, as if it had only been waiting at a distance. With light comes movement. Particles become visible again. Shapes gain edges. Depth becomes something that can be seen rather than calculated. The environment grows busier, not suddenly, but steadily. Life becomes more frequent, more varied, more responsive. The stillness of the trench gives way to a layered hum of activity. The ascent does not erase what was learned below. It carries it upward, reframed rather than replaced. Pressure, darkness, scarcity, chemistry, sound, and patience remain part of the understanding, even as conditions change. The deep does not end, it recedes. What remains most striking after spending time at the bottom of the world is not how extreme it is, but how consistent. The trench does not fluctuate, it does not surprise. It exists within limits that are narrow but stable. In that stability, life has found ways to persist without spectacle, without urgency, without excess. Returning toward the surface highlights how unusual the surface actually is. the rapid changes, the abundance of energy, the constant motion. The deep reveals these as exceptions rather than norms. Most of the planet exists closer to the trench's pace than to the surface's speed. This realization has a quiet weight to it. It does not demand action or resolution. It simply adjusts perspective. It reminds us that the world beneath our feet and beneath the oceans operates on timelines and principles that are not designed around human attention. The Earth does not hurry. As the ascent continues, familiar ideas regain relevance. Day and night matter again. Weather returns, sound sharpens, time resumes its familiar rhythm. But the knowledge of what lies below does not fade with altitude. It lingers as context. The Mariana Trench does not ask to be remembered. It does not need recognition. It exists whether it is known or not. But knowing it changes how the rest of the planet feels. It adds depth not just to maps, but to understanding. It becomes harder to think of the ocean as a surface, or the Earth as a thin shell. It becomes harder to believe that distance equals separation, or that invisibility equals insignificance. The trench quietly undermines those assumptions by existing in a way that is both extreme and ordinary at the same time. There's also a sense of continuity that emerges. The deep ocean has always been there, long before humans measured it, long before it was named, long before the idea of a bottom had meaning. It will remain long after current concerns shift, after technologies change, after surface priorities rearrange themselves again and again. This does not make the trench indifferent in a dismissive way. It makes it consistent. It follows rules that do not adapt to opinion or urgency. Pressure does not negotiate. Darkness does not compromise. Scarcity does not apologize. Life adjusts or it does not continue. That clarity can feel stark, but it can also feel grounding. It strips away the illusion that everything must be fast, visible, or dramatic to matter. The deep matters precisely because it is slow, hidden, and patient. As the surface draws closer, there is no sense of leaving something behind. The trench does not feel like a place exited, but a context carried. It remains beneath, shaping currents, chemistry, and perspective whether or not it is actively considered. Human life resumes its usual scale quickly. Conversations, schedules, screens, and obligations return. The pace accelerates. Attention fragments. But somewhere beneath all of that, the deepest place on Earth continues its quiet existence, unaffected by surface urgency. This contrast does not diminish surface life. It situates it. It reminds us that the world is larger, deeper, and more layered than daily experience suggests. That meaning does not always arrive through intensity. Sometimes it arrives through steadiness. The Mariana Trench does not offer closure. It does not conclude anything. It simply exists, continuing its slow dialogue with gravity, chemistry, and time. Rising away from it does not end that dialogue. It only changes where it is heard. And so the ascent completes not with an ending, but with a return to balance. Light above, depth below, motion at the surface, stillness beneath. All of it happening at once, connected, layered, and ongoing. The deep remains where it has always been, not waiting, not retreating, just present. And the surface, for all its movement and noise, rests quietly on top of it, whether it remembers that fact or not.